Imagine you're a geologist, and it's 50 million years from now. You're drilling through layers of rock trying to piece together what life looked like on this planet. You pull up a core sample and you find something strange, a thin layer of unusual chemistry, carbon ratios that don't quite match anything natural, trace metals in concentrations that seem almost impossible. And then you hit something you've never seen before, a microscopic sliver of material that shouldn't exist at all. You'd stop and you'd think, did something happen here? Was something here? Now flip that around. What if something did happen here long before us? What if there was an industrial civilization on Earth? Not aliens, not Atlantis, just another species millions of years before humans ever walked out of Africa, and the geological record has had so long to erase the evidence that we'd barely know where to look. That question, seriously asked by two NASA and university scientists in 2018, is called the Silurian Hypothesis. And before you close the tab, this is not a conspiracy theory. It is not a claim. It is one of the most rigorous, careful, quietly mind-bending thought experiments in modern science. And the more you understand how the Earth stores and destroys its own memory, the more unsettling the question becomes. If you're listening to this to drift off tonight, that's exactly what this channel is built for. Drop a comment and tell me where you are and what time it is. I genuinely read them, and it never gets old. Someone in Tokyo at 6 in the morning, someone in Toronto pulling a late shift, someone in Melbourne who can't sleep, all listening to the same question at the same moment. There's something about that I find extraordinary. And if you want to support the channel, the best way is to follow History for Sleep on Spotify and listen there. The link is in the description. It helps more than you'd think. Now back to the hypothesis. The scientists who proposed it, Gavin Schmidt at NASA and Adam Frank at the University of Rochester, weren't claiming they had found evidence of a prior civilization. They were asking something more precise and more disturbing. If an industrial civilization had existed tens of millions of years ago, what would it actually look like in the rock record today? Would we even recognize it? And what does our own civilization right now look like to a geologist of the deep future? Those two questions turn out to be the same question. And to answer them, you need to become a kind of detective, not of crime scenes, but of deep time. The tools are geology, chemistry, isotope ratios, fossilized biology, and the Anthropocene itself, which turns out to be the most useful test case we have. Over the next several sections, we're going to move carefully through the evidence, or rather through the framework for what evidence would even mean across millions of years. We'll look at what survives, what vanishes, and what signatures a technological species almost inevitably leaves behind. And we'll be precise about language throughout, because this is a subject that demands it. There's a difference between possible, plausible, and probable, between a signal and a coincidence, between a hypothesis and a discovery. The question isn't whether we're the first. The honest answer is, we don't know. What's interesting is figuring out how we'd ever find out. So let's start with what the hypothesis actually is, because the name alone invites misunderstanding. The Silurian hypothesis is not a claim. It is not a theory in the colloquial sense of that word, meaning a hunch or a suspicion or something a guy said on a podcast. It is a precisely framed scientific question, published in the peer-reviewed International Journal of Astrobiology in 2018, and the question is this: given what we know about how the geological record forms and degrades over millions of years, would we even be able to detect the existence of a prior industrial civilization on Earth if one had existed? That's it. That's the whole thing. The hypothesis is not arguing that such a civilization existed. It's asking whether we'd know if it had. Those are very different statements, and keeping them separate is the first and most important thing you can do if you want to think clearly about this subject. Gavin Schmidt and Adam Frank, the two scientists who formalised the question, are not fringe researchers. Schmidt directs NASA's Goddard Institute for Space Studies. Frank is an astrophysicist at the University of Rochester who studies planetary habitability. When they wrote the paper, they were explicit about what they were and weren't doing. They were establishing a framework, a set of criteria, a kind of checklist for what geological signals an industrial civilization would plausibly leave behind, and then asking whether those signals would survive millions of years of geological processing. They were also crucially doing this to sharpen our understanding of the Anthropocene, which is the name scientists give to the current geological epoch defined by human impact on the planet. Understanding what our civilization looks like from the deep future turns out to require understanding what any civilization would look like from the deep future. Now the name, why Silurian? The Silurian period ran from roughly 443 to 419 million years ago. It was a fascinating time in Earth's history. The first vascular land plants were establishing themselves. Fish with jaws were diversifying. The first coral reefs appeared. It was, by most measures, a world in transition from ocean-dominated to land-colonized life. But here's what it was not. It was not a period with anything remotely resembling intelligent life. There were no mammals, no reptiles, no creatures that could plausibly build a civilization. The most complex animals on land in the Silurian were early arthropods and millipede-like creatures. The seas had jawless fish and armoured fish, and a remarkable diversity of invertebrates, but nothing with the neural complexity even remotely required for technology. So why call it the Silurian Hypothesis? The name is borrowed from a Doctor Who episode, specifically a classic serial, featuring a fictional species called the Silurians, a race of intelligent reptiles who supposedly dominated Earth hundreds of millions of years ago and retreated underground when a catastrophe struck, eventually awakening in the modern era. Schmidt and Frank borrowed the name as a kind of knowing, playful nod to science fiction, a way of signalling that the question sounds outlandish while also being rigorous. They were essentially saying, yes, we know this sounds like the plot of a TV show. We're asking it anyway, because the science of deep time detectability is real and important, regardless of the fantastical framing. The name has nothing to do with the Silurian period specifically. The hypothesis is not claiming that civilization arose 430 million years ago. It's asking about any prior period, and more specifically, about whether the geological record is even capable of preserving the right kind of evidence. Now here's where we need to draw some careful lines, because there are several things the Silurian hypothesis is often confused with, and the confusion matters. First, this is not a hypothesis about a prior human civilization. We have an extremely good fossil and genetic record for hominins going back several million years. We know when our genus appeared, we know when the first stone tools were made. We know the rough timelines of every major transition in human evolutionary history. There is no gap in that record large enough to hide a technologically sophisticated human society. If the hypothesis is asking about anything, it's asking about a different species entirely, one that evolved intelligence independently long before anything like a primate existed, and then vanished completely enough that its biological lineage left no obvious trace either. Second, and this is important, this is not a hypothesis about mythic lost continents. Not Atlantis, not Lemuria, not Mu. Those are stories, some ancient, some invented in the 19th century, none of them supported by geological evidence, and all of them involving human or near-human civilizations in the relatively recent past, a few thousand to tens of thousands of years ago. That time frame is actually the easiest to investigate, geologically speaking. We have ice cores, sediment records, and archaeological preservation at those timescales that are remarkably detailed. There's no room for a lost advanced human civilization there. We'd have found it. The Silurian hypothesis is asking about deep time. Not 10,000 years ago, not 100,000. Millions of years, tens of millions, maybe more. And at those timescales, the geological record behaves very differently. Which brings us to what is probably the single most important physical constraint in this entire discussion. The Earth is not a good archivist. Rock is constantly being formed, transformed, and destroyed. The process called plate tectonics means that oceanic crust, the kind that covers most of the planet's surface beneath the oceans, is continuously being created at mid-ocean ridges and destroyed at subduction zones, where it dives back into the mantle and melts. The average age of the oceanic crust is only around 60 to 70 million years, which means anything sitting on that crust that's older than roughly 60 to 70 million years has almost certainly been dragged into the Earth's interior and ceased to exist. Continental crust is older and more stable, but it too erodes, metamorphoses under heat and pressure, gets buried, uplifted, and reworked over geological time. The practical consequence is this: the further back you go, the less of the original record survives. And the record that does survive has been filtered, compressed, and altered in ways that make interpretation genuinely difficult. A thin anomalous layer in a rock formation might represent 10,000 years of unusual chemistry, or it might represent a single catastrophic event, or it might be an artifact of how the rock was transformed after deposition. Telling those apart requires careful work, and even then, ambiguity often remains. Schmidt and Frank were very explicit about this constraint. They weren't just asking whether an ancient civilization's buildings or roads or artifacts might survive millions of years. That's actually the easy part to dismiss. Physical structures at that timescale would be almost certainly gone. What they were asking is whether the chemical and isotopic signatures of an industrial civilization, the things a technological species does to the atmosphere, the oceans, the carbon cycle, the nitrogen cycle, could leave traces in the rock record that would be detectable and interpretable tens of millions of years later. And here the question becomes genuinely subtle, because some signatures are stronger than others, and understanding that hierarchy is what the rest of the hypothesis is really built around. Strong signals are things that would be globally distributed, chemically distinctive, and would require an explanation that natural processes struggle to provide on their own. A sudden worldwide spike in specific isotope ratios with no known natural cause, occurring simultaneously across multiple continents in multiple rock types, would be a strong signal. It would demand an explanation. Weak signals are things that could plausibly arise from natural processes acting alone. A slight increase in heavy metals in a particular sediment layer might mean industrial pollution, or might mean a volcanic event, or might mean changes in ocean chemistry during a period of anoxia. One line of ambiguous evidence means almost nothing. Ambiguous signals are things that would point toward an explanation without ruling out alternatives. They can be suggestive, they can focus investigation, but they can't stand alone. What Schmidt and Frank were really doing, at the deepest level, was trying to establish what kind of evidence would actually be convincing. What combination of signals would make a geologist stop and say this can't be natural? Something made this. And in doing that, they were also implicitly asking what our own civilization looks like in those terms. Right now, today, what signals are we generating that are strong enough to survive millions of years of geological recycling and still be recognizable as the product of a technological species? The answer to that question turns out to be both reassuring and quietly unsettling, depending on how you look at it. We are leaving marks. Some of them will last. The question of which ones and how legible they'll remain is what we're going to spend the rest of this conversation exploring. To make sense of the Silurian hypothesis, we have to learn to read the planet the way a geologist does. Not as a static globe of rock, but as something more like a palimpsest, a manuscript written, scraped off, and written over again. If you want to hide a civilization, deep time is your best ally. But if you want to find one, you start by asking a deceptively simple question. Where on Earth does memory actually accumulate? It's not everywhere. Most of the land surface you see today is terrible at long-term storage. Mountains shed their skin in rockfalls and landslides. Rivers chew their banks, pick up sediment, and carry it away. Even seemingly solid plains are being slowly reworked by frost, roots, burrowing animals, wind and water. The ground under your feet is busy. The real archives form where sediment comes to rest and stays put for a long time. Think about rivers. They erode upstream, carrying grains of sand, bits of clay, organic debris. When the river slows at its mouth, or where it spreads into a delta, it drops that load. Year after year, flood after flood, layer after layer, the pile grows. Deltas and coastal basins are some of Earth's great filing cabinets. Each new layer of mud or sand is like a thin page laid gently on top of the last. In those layers you can capture pollen, shells, microfossils, bits of charcoal from ancient fires, tiny droplets of polluted ash, even molecules of industrial chemicals if they existed. Lakes do something similar on a calmer scale. In quiet, deep lakes, fine particles settle like dust in a room that's never cleaned. In some of them you can see distinct annual bands, dark organic rich layers from summer, pale mineral layers from winter. Over thousands of years those seasonal lines blur together into thicker packages, but they still hold a story. Changes in climate, shifts in vegetation, periods of erosion, phases of anoxia when the bottom waters lost oxygen. Then there are the oceans. Most of the long-term memory on this planet sits beneath water. Slow rain of microscopic shells sinks through the water column to the seafloor. Dust blown from continents, ash from volcanoes, soot from fires, all of it eventually arrives at the bottom of some basin somewhere. On the abyssal plains, far from shore, sediment can accumulate at just a few millimeters per 1,000 years. In places like continental margins and deep ocean basins, it can stack up faster. Over tens of millions of years, those millimeters add up to hundreds of meters, even kilometers, of layered archive. When we drill ocean cores or lake cores, we're unrolling part of this archive, line by line, layer by layer. That's where we see past climate cycles, abrupt warming events, mass extinctions, and the subtle chemical fingerprints of things that happened long before any human existed. If an industrial civilization had ever reshaped its atmosphere, dumped chemicals into rivers or burned vast amounts of biomass, the best chance of its marks surviving would be in places like these, quiet basins where sediment gently buries the past. But that's the optimistic side of the story, the archival side. The other half is destruction. The same processes that deliver sediment also tear old layers apart. Erosion is constantly shredding Earth's pages. Mountains rise, but as soon as they do, rivers begin soaring into them. Glaciers scrape entire valleys down to bedrock and haul their rubble away. Coastlines advance and retreat with sea level, drowning old landscapes and then stripping them bare again when the water falls. Even the basins themselves don't last forever. A lake can fill in and turn into a swamp, then a meadow, then a forest. A delta can shift course, abandon one lobe and build another somewhere else, leaving its old sediments to be dissected by new rivers. From the perspective of a future geologist, this means our planet's history comes in fragments. 100,000 years preserved here, 1 million there. then a gap of unknown length where erosion removed what had once been recorded. Below the surface, the editing gets even more ruthless. Continental crust can be old billions of years in some places, but it's not untouched. As plates move, crust is buried, heated, squeezed, and sometimes partially melted. This is metamorphism, the slow cooking and recrystallizing of rocks under heat and pressure. When a rock is metamorphosed, its minerals change. Its original textures blur. Fossils can be stretched, smeared, or obliterated entirely. Chemical signals can be reset. It's as if you took a book and pressed it in a hot vice until the ink bled and the pages fused. And oceanic crust has an even harsher fate. It doesn't just get cooked, it gets eaten. New ocean crust forms at mid-ocean ridges, spreads outward, cools, and eventually meets a subduction zone, a place where one plate plunges back into the mantle. As it goes down, the sediments on top of it are scraped off, squashed, folded, and sometimes plastered onto the edge of continents. The rest is dragged beneath and heated until it melts or deforms beyond recognition. This is how you recycle a planet. On human timescales, the sea floor feels ancient and permanent. On geological timescales, it's more like a conveyor belt transferring everything back into the deep interior. The average age of ocean crust is on the order of tens of millions of years. Not billions, which means that if you go back far enough past the time of the dinosaurs, past the great coal swamps, past most of the complex life we know, essentially every piece of seafloor that existed then has been destroyed. Whatever sat on that seafloor is gone with it. The continents fare better, but even they don't keep everything. Large parts of older continental crust have been deeply buried, metamorphosed, or eroded away. The patches we can read clearly are like surviving paragraphs of an ancient epic, quoted and recopied across different manuscripts. We know there was a story. We don't have every page. On top of all this, there's another complication: time averaging. When you look at a rock layer that's, say, 10 centimeters thick, it's tempting to think of it as a moment in time, a snapshot. In reality, it often represents thousands, sometimes tens of thousands of years of gradual accumulation. Events that were sharp and brief when they happened get smeared out in the geological record. A few centuries of extremely unusual conditions can end up diluted into a single, somewhat odd-looking band. One catastrophic flood might occupy a millimetre or two. 1,000 years of industrial activity might be blended into a decimetre of mud. This blurring matters for the Silurian hypothesis. Because we're not just asking, would anything be preserved? We're asking, would it stand out? Imagine a future geologist studying a 10-centimetre layer that represents 20,000 years. If an industrial civilization burned fossil fuels for only 500 of those years, a brief flare in deep time, its chemical fingerprint would be averaged across the whole thickness. The spike in, say, carbon isotopes or heavy metals might still be there, but it would be muted, softened, harder to distinguish from the background noise of natural variability. Now zoom out even further. Earth is about 4.5 billion years old. But most of the solid surface that we can examine in detail, rocks at or near the top of the continents, sediments on the seafloor, accessible outcrops, is much younger than that. There are ancient cratons, continental cores, that go back more than 3 billion years, but their upper layers have usually been reworked many times. The continuous fine-grained records that geologists love, lake sequences, ocean sediment stacks, are often limited to the last few 100 million years, and even within that interval they're full of hiatuses and interruptions. If you drew Earth's history as a long bookshelf, it wouldn't be a neat, complete run of volumes, from volume 1 to volume 4.5 billion. It would be more like a few shelves of intact books, some charred covers with pages missing, and long, suspiciously empty stretches where you know something should be, but the space is blank. This is why the question Schmidt and Frank posed is not silly. If you want to know whether an earlier industrial civilization could have existed, you first have to face how little of the planet's surface history is actually available for inspection, and how coarsely that history is recorded. You have to accept that we're working with incomplete archives that have been shredded, cooked, averaged, and sometimes entirely recycled. And once you accept that, the next step is to ask a very practical question. Given these limitations, what kinds of traces are robust enough to survive all this editing? What signals can persist through erosion, metamorphism, subduction, and time averaging, and still whisper, something unusual happened here? Those are the signals we'll follow next, as we ask what an industrial civilization, ours or anyone else's, would really leave behind in the rock. So imagine you're that future geologist drilling a core through some anonymous layer of mud that used to be our present. What are you actually hoping to see? Not skyscrapers, not silicon chips, not rusted cars. Those are fragile, local, and easy for erosion and tectonics to erase. What you're looking for are patterns that are global, or at least widespread. Things that don't care whether a city gets ground down because they're written into the chemistry of the whole planet. The first place you look is carbon. An industrial civilization that burns buried carbon, coal, oil, gas, even giant peat deposits, can't help but shove the carbon cycle out of balance. In the rock record, that kind of disturbance shows up in two main ways: how much carbon there is, and what kind it is. The what kind part is about isotopes. Carbon comes in different flavors, mainly carbon-12 and carbon-13. Plants prefer carbon-12. Fossil fuels, which are just very old plant matter, are therefore rich in carbon-12. When you burn a lot of it in a short time, the atmosphere and oceans shift toward that lighter isotope. Geologists see this as a negative carbon-13 excursion, a sudden drop in the ratio of carbon-13 to carbon-12 in carbonates and organic matter. On its own, that doesn't prove industry. Volcanoes, methane releases from the seafloor, and massive wildfires can also change the carbon-13 balance. But the pattern matters. How fast the shift happens, how big it is, how it lines up with temperature changes, oxygen levels, and other signals. Then there's the total amount of carbon locked into sediments. If an industrial civilization triggered global warming, it could push the climate system toward more fires, more erosion, more organic matter washed into basins, or, under some conditions, toward widespread oxygen-poor waters where organic carbon gets buried instead of decomposed. Either way, a core might show a band where both the quantity and the isotopic flavor of carbon look odd. But carbon isn't the only cycle industry meddles with. Modern humans have taken the nitrogen cycle, once controlled mostly by microbes and lightning, and supercharged it. Synthetic fertilizers pull inert nitrogen from the air and turn it into reactive compounds. Some of that feeds crops. A lot of it washes into rivers and coasts where it can create blooms of algae and dead zones in the sea. In sediments, this kind of disruption can leave several overlapping traces: elevated nitrogen content, unusual ratios of nitrogen isotopes, and evidence of repeated low oxygen events in coastal waters. If an earlier civilization developed intensive agriculture or large-scale waste streams, you might expect to see something similar: a spike in fixed nitrogen, perhaps paired with changes in phosphorus, another nutrient humans mine and move on a planetary scale. Heavy metals add another layer to the menu. Many industrial processes concentrate elements that are normally rare and widely dispersed. Lead, mercury, cadmium, chromium, copper, rare earth elements. Modern society digs them up, purifies them, and then scatters a fraction of them into the air, water and soils. in a sediment core that could appear as thin intervals with anomalously high concentrations of specific metals, often accompanied by tiny grains of industrial ash or fly ash spheres. Some metals are mobile and can be rearranged by groundwater later on. Others tend to lock into mineral lattices and stick around. Over millions of years, metamorphism can blur these patterns. But in younger, less altered rocks, a synchronized, globalish jump in certain metals would be a red flag. Something technological was stirring the pot. Then there are chemicals that nature simply doesn't make. Our civilization produces an entire zoo of synthetic molecules, from chlorofluorocarbons to complex plastics to long-lived fluorinated compounds. Most of them are unstable on geological timescales. Sunlight, oxygen, microbes and heat break them down. But breakdown doesn't always mean disappearance. It often means transformation. A plastic bottle left on a beach fractures into microplastics, then nanoplastics, then eventually into simpler hydrocarbons that might bind to clays or get baked into new minerals. A fluorinated compound might lose some of its bonds but leave behind distinctive fluorine-rich residues that are rare in natural settings. If a past civilization had its own version of synthetic chemistry, the exact compounds would be different. But the logic would be the same. Highly unusual molecules, mass-produced and globally dispersed, would decay into families of byproducts. Some fraction of those byproducts would be tough enough to be preserved in sediments as odd organic signatures or peculiar enrichments in certain halogens or trace elements. The key isn't that you'd find an intact plastic bag 100 million years from now. It's that you might find a thin horizon where the organic molecules look subtly but systematically wrong compared to what biology and geology usually cook up on their own. Running alongside all of this are radiogenic and isotopic hints that something strange happened. Industrial societies play with radioactive materials. They dig up uranium, concentrate it, burn it in reactors, and sometimes spread fallout through weapons testing or accidents. Even after the short-lived isotopes decay away, they leave behind disequilibria in decay chains, excesses of certain daughter products, and subtle distortions in isotope ratios of elements like plutonium, cesium, or strontium. Natural processes can also enrich or fractionate isotopes. Volcanoes, hydrothermal vents, cosmic rays, all of these leave their own fingerprints. But a civilization that mined, refined, and redistributed huge amounts of specific isotopes could imprint a pattern that doesn't quite match any known natural analogue, a thin worldwide layer where multiple radiogenic anomalies coincide. Notice something about all these markers. They're not skyscrapers. They're not fossil cars. They're chemistry. Physical artifacts are spectacular to us because we live among them. But they're local and fragile. Cities tend to sit on coasts and river plains, places that erode, flood, and subside. In a few 100,000 years, most surface structures become gravel and clay. In a few million, they are either buried beyond easy reach or have been chewed up and recycled. Global signals don't care where the cities were. They're carried by air and water, and they fall out everywhere. Into lakes, deltas, deep ocean basins. Even if 99.9% of the planet's surface history is lost, the surviving scraps are more likely to include those broad chemical and isotopic shifts than the foundations of a single building. And there's one more category of evidence that a technological species can't help but disturb: life itself. An industrial civilization, especially one that practices agriculture, tends to reshape ecosystems. It domesticates some species, drives others extinct, and moves organisms around the globe. Over time, this leaves a peculiar biosignature. Fossils might show sudden expansions of a few hardy generalist species into regions where they were previously rare or absent, equivalents of rats, pigeons, or invasive weeds. Pollen records might reveal monotonous landscapes dominated by a handful of cultivated plants. Shell beds could shift as certain marine organisms boom in nutrient-rich waters, while more sensitive species vanish. At the same time, extinction patterns might tilt in odd ways. Large animals disappearing faster than expected, certain habitats collapsing rapidly while others remain relatively intact. The rock record of our own time, for instance, is likely to show a sharp, selective loss of big vertebrates and specialized species, paired with a spread of human-associated organisms and pathogens. Put all of this together, and the menu of signatures starts to look like a combined chemical-biological fingerprint. You're not just looking for a carbon anomaly, you're looking for a carbon anomaly that lines up with nitrogen distortions, heavy metal spikes, weird organic molecules, radiogenic oddities, and a sudden selective reshuffling of the biosphere. Any one of those can have a natural cause. Volcanoes can dump metals. Methane can shift carbon isotopes. Tectonics can change ocean oxygen levels and drive extinctions. But a tightly clustered suite of changes, all crammed into a relatively thin slice of time, pointing in the same direction, that begins to look less like random coincidence and more like a planet that briefly hosted something industrial. In the next sections, we'll turn that lens back on ourselves and ask a slightly uneasy question. If future geologists drilled through the sediments of the Anthropocene, what exactly would they see? To answer that, we don't have to guess. We're living through the experiment right now. Geologists sometimes call the last century and a half the Great Acceleration. In graph form, it looks almost comical. For most of human history, curves of population, energy use, fertilizer production, dam construction, car numbers, global trade all hug the bottom of the chart. Then, somewhere around the mid-20th century, they kink upward into near vertical spikes. If you saw that shape in a rock core from deep time, a whole bundle of different variables, all flipping from flat to steep at almost the same moment, you'd stop what you were doing. In our case, that kink starts in the late 19th century with coal and industrialization, then sharpens dramatically after World War II. In just a few generations, we've dumped more carbon into the atmosphere than natural processes would normally move in thousands of years. We've mined and scattered metals that had spent hundreds of millions of years locked in ores. We've made entirely new molecules and spread them from polar ice to deep-sea mud. From a geological perspective, it's like a flashbulb going off. You can see it first in greenhouse gases. CO2 levels meandered between about 180 and 280 parts per million over the last 800,000 years, tracking ice ages and warm periods in a relatively gentle rhythm. Then, starting around 1850, the curve breaks character. It shoots past 300, 350, 400 parts per million, headed toward levels not seen in millions of years. Methane, which had also followed a slow natural dance, does the same thing, doubling in concentration in a geological eye blink. But it's not just the amount that changes, it's the flavour. Remember that plants prefer carbon-12, fossil fuels, being ancient plant matter, are skewed toward that lighter isotope. As we burn them, the extra carbon-12 dilutes the atmospheric and oceanic carbon-13. When future geologists analyse carbonate shells or organic matter from our time, they'll see a sharp negative delta-13C excursion, a distinctive downward wiggle in the carbon-13 to carbon-12 ratio. It will be unusually fast, on the order of centuries instead of the thousands of years typical for big natural carbon perturbations. It will coincide with warming, with ocean acidification, with changes in oxygen levels. It will sit right on top of a suite of other disturbances. One of those is our most humble inheritance, trash. Plastics and microplastics are turning into a novel kind of sediment. They wash off land, sink in rivers, drift into estuaries, and rain down onto the seafloor. Beach sands now mix grains of quartz with coloured plastic fragments. Deep-sea cores already show layers where synthetic polymers are embedded alongside diatom shells and volcanic ash. Over time, individual objects will disintegrate, but the particles don't vanish, they fragment. Centimetre pieces become millimetre shreds, then microscopic flecks, then nanoplastic dust. Some of that will be oxidized or digested away. Some will be locked into mineral cements, trapped in pore spaces, or preserved in anoxic muds. A thin stratum of the future rock record may literally be a plastic-rich conglomerate, a technogenic layer where polymer residues, odd organic molecules, and their breakdown products form a chemical fabric unlike anything purely biological. Even the dust we make looks different. Industrial fly, ash, soot, tire wear, metal-rich aerosols, all of these produce tiny, distinctive particles that drift globally and settle out of the sky. Under a microscope, they show up as perfectly spherical carbonaceous grains, glassy cenospheres, and metal-coated fragments. In recent sediments, they already form characteristic horizons. Given the right conditions, rapid burial in low-oxygen basins, those man-made particles could be frozen in place as a kind of microscopic index fossil for our age. Then there's the sharpest timestamp of all, radionuclides. In the early 1950s, humans began detonating nuclear weapons in the atmosphere. Each blast lofted a stew of fission products, and neutron-activated isotopes high into the stratosphere, where winds smeared them around the globe. They rained out in a worldwide pulse onto oceans, lakes, ice caps, soils. That fallout peak, concentrated in the early 1960s, is now one of the cleanest global markers we've ever produced. Sediment cores from Arctic lakes, coral skeletons, even tree rings show simultaneous spikes in isotopes like cesium-137, plutonium-239, and carbon-14. Many of those nuclides are short-lived on geological scales. In a few 100,000 years, most will have decayed away. But decay doesn't erase the disturbance entirely. It leaves behind subtle excesses of certain daughter products and decay chain imbalances. And crucially, the original distribution is incredibly abrupt in time. To a future stratigrapher working in rock rather than mud, that might appear as a razor-thin band, where multiple radionuclide anomalies once coincided, a timeline you could trace around the world. So, if all of this is so dramatic, does that mean our civilization is guaranteed to be obvious tens of millions of years from now? Not necessarily. The same forces that bury evidence also blur it. Plate tectonics will drag large chunks of today's seafloor down into the mantle. Mountain building will squeeze and heat sediments until minerals recrystallize and isotopic gradients smear. Groundwater will mobilize some metals, redistribute others, and overwrite delicate chemical contrasts. Plastics will not survive in their current form. Most synthetic molecules will be long gone. The neat separation between pre-industrial and industrial layers may be folded, faulted, or eroded into patches. In many places, the entire Anthropocene package might be stripped away before it ever has a chance to turn to rock. But lost everywhere is different from lost somewhere. Our signal is extraordinarily intense and globally spread, even if it's thin. That combination gives it a decent chance of surviving in at least a few protected archives, deep ocean basins that escape subduction for tens of millions of years, rapidly buried lake beds, subsiding continental margins. In those places, the great acceleration may remain legible as a compressed but unmistakable chemical glitch, a strange, brief flicker in Earth's long memory. And that flicker is exactly what the Silurian Hypothesis asks us to think about. If our own industrial burst leaves only a blurred centimetre-thick echo in some future core, What would we expect from a civilization that rose and fell not thousands, but tens of millions of years before us? To answer that, we need to look more closely at some of our strongest markers, starting with carbon itself. To see why carbon is such a powerful clue, we have to zoom in on that little symbol we just met, delta the 13C. In plain terms, delta 13C is just a way of saying how much carbon-13 is there compared to carbon-12 relative to a standard. It's written as a number of parts per thousand, positive or negative. But you don't need to care about the math, you just need the story behind it. Plants are picky eaters. When they pull carbon dioxide out of the air, their enzymes grab carbon-12 more easily than carbon-13. Over time, that means plant tissues and anything that eats plants, and anything that eats the plant eaters, all end up slightly depleted in carbon-13. Their delta the 13C number is a bit more negative than the atmosphere they grew in. Fossil fuels are nothing but very old, very cooked plant carbon. Coal, oil, natural gas, they've all been filtered through that biological preference for carbon-12. So when we dig them up and burn them, we're taking carbon that is isotopically light and dumping it back into the fast carbon cycle. To a geochemist, that looks like this. The total amount of carbon in the atmosphere and ocean goes up, and the delta the 13C value goes down. On a graph, it's a sharp downward spike, a negative delta 13C excursion. You can see it in the tiny shells of plankton that rained down through the water column. You can see it in cave deposits. You can see it in organic matter locked into muds. But the key isn't just that the line goes down, it's how fast. Natural carbon cycle changes do this too. Volcanoes belch CO2 that's closer to the mantle's isotopic mix. Massive blooms of life can suck carbon out of the surface ocean, altering delta the 13C in the remaining water. The burial of huge amounts of organic carbon can push delta the 13C in the opposite direction, toward heavier values. Those are big swings. Some past events show delta 13C drops of 3, 4, even 5 parts per thousand. What makes our signal stand out is that we're driving a noticeable shift in a couple of centuries. Many ancient perturbations took thousands to tens of thousands of years. Fast carbon injection has predictable side effects. More CO2 traps more heat, so global temperatures rise. Warmer oceans absorb less CO2, which amplifies the rise further. Dissolved CO2 forms carbonic acid, which lowers ocean pH, making it harder for corals, foraminifera, and other shell builders to maintain their carbonate skeletons. In sediments, you start to see thinner, more fragile shells or intervals where carbonate simply dissolves away, leaving clay-rich layers. At the same time, warmer, more stratified oceans can lose oxygen at depth. That produces dark, organic, rich muds, future black shales in places that once had well-oxygenated bottom waters. Combine all of that, and a rapid carbon release shows up as a package, a negative delta the 13C excursion, warming, acidification, and changes in sediment type and microfossils. That's the sort of bundle we'd be hunting for if we were looking for someone else's Anthropocene. But there's a snag, several actually. First, a hypothetical earlier civilization might not lean on fossil fuels the way we did. They might develop solar, wind, geothermal, or some alien to us energy source long before they stumble onto coal seams. They might learn very early that burning ancient carbon is a bad idea and leave most of it underground. In that case, their industrial footprint could be technologically dramatic but isotopically modest. A lot of metals, weird molecules and habitat change, but only a small tweak to global DA13C. Or they might burn biomass instead of fossil fuels. Wood, crop residues, algal fuels, that carbon has only been out of the atmosphere for years to centuries. When you burn it, you're mostly recycling recent carbon, not injecting new geological stores. The total amount of CO2 in the air can still rise if you clear forests and destroy soils, but the isotopic signal looks different. It's more like reshuffling what's already there than tapping a deep reservoir. From far in the future, that kind of disturbance might blur into the background of natural climate variability. And even if they did burn fossil fuels, nature offers several convincing impersonators. Large igneous provinces, immense outpourings of basalt linked to mantle plumes, can intrude into organic-rich rocks, cooking coal beds and oil shales in place. That releases vast amounts of light carbon in geologically short bursts. Methane hydrates, frozen on the seafloor, can destabilize during warming episodes, belching CH4 into the ocean and atmosphere. Methane is extremely depleted in carbon-13, so its release causes sharp negative delta-13C excursions too. Orbital cycles, continental rearrangements, and feedbacks in weathering can all reconfigure the carbon cycle without any help from technology. The Paleocene-Eocene thermal maximum 56 million years ago is the classic example. A rapid warming, a big negative deal to the 13C shift, ocean acidification, and biotic stress. It looks disturbingly familiar, but most researchers think it can be explained by a combination of mantle-derived CO2 methane hydrate release and feedbacks in the natural system. So what would make a civilization like Carbon Signal stand out from all that? You'd look for a few things lining up at once. An unusually abrupt negative delta the 13C excursion compressed into centuries to a few millennia. A corresponding spike in CO2 and warming. That's steep compared to similar background cycles. Clear evidence of widespread ocean acidification and oxygen loss. And crucially, a coincidence with other weird markers, unfamiliar organic molecules, anomalous metal distributions, odd patterns in fossils and sediments that suggest rapid land use change rather than slow tectonic forcing. You'd also look for asymmetry. Natural events often have somewhat smoother rise and fall timescales, or are paced by orbital rhythms. A technologically driven carbon pulse might be incredibly fast on the way up, then linger or decline in a way tied to social collapse, resource limits, or deliberate mitigation, patterns that don't neatly match volcanic or orbital behavior. Even then, certainty would be hard. With only chemistry in hand, the line between planet gone rogue by itself and planet nudged by its own clever organisms can be blurry. That's why carbon, for all its power, can't be the only line of evidence. To really test the Silurian hypothesis, we'd need to stack multiple independent clues on top of each other. The next layer in that stack comes from something far less glamorous than carbon: fertilizer. If carbon tells us about energy, nitrogen, and phosphorus, tell us about food. Modern industrial civilization doesn't just run on electricity and gasoline. It runs on fertilizer. Without it, the number of humans this planet can support drops dramatically. And that obsession with boosting plant growth leaves its own kind of fingerprint. Start with nitrogen. Most of the nitrogen on Earth is locked up in the air, floating by as N2 gas. Plants can't use that directly. They need fixed nitrogen, nitrate and ammonium, already broken apart and recombined into reactive forms. For most of Earth's history, that job was done slowly and locally: lightning, a few specialized microbes, some minor industrial chemistry in volcanoes and wildfires. Then, in the early 20th century, we invented the Haber-Bosch process. We learned to grab that inert nitrogen from the sky, smash it together with hydrogen at high temperature and pressure, and turn it into ammonia, into fertilizer. From a planetary perspective, that is stunningly unnatural. In just over a century, humans doubled the rate at which reactive nitrogen is added to the land surface each year. We turned ourselves into a geologic force, rewriting the nitrogen cycle. Geochemists can see that in isotopes. Nitrogen also comes in multiple flavors, mainly nitrogen-14 and nitrogen-15. Biological processes, sewage, and synthetic fertilizers all leave subtle but distinctive signatures in the ratio between them. When we mine the atmosphere for nitrogen and dump it in concentrated form onto fields, into rivers, and out of smokestacks, we alter those ratios at large scale. Today, sediments in lakes, estuaries, and coastal zones are recording this. Layers laid down over the last 100 years often show a marked shift in nitrogen isotopes, consistent with huge inputs of artificial fertilizer and human waste. In some cores, you can literally see the transition. Older layers shaped by natural cycling, younger ones stamped by agriculture and industry. But it's not just the numbers that change, it's what that excess nitrogen does when it runs downhill. Most of the fertilizer we spread doesn't stay politely in the soil. Rain washes it into streams and rivers, which carry it to lakes and seas. There, along with phosphorus, it acts like a supercharged multivitamin for algae. Too many nutrients, and you get eutrophication, explosive algae blooms that eventually die, sink, and rot. Bacteria chewing through all that dead organic matter suck oxygen out of the water. Fish flee if they can. Anything that can't move fast enough suffocates. On a map, these are the dead zones, stretches of coastal ocean, like the one at the mouth of the Mississippi, that go hypoxic every year. On the sea floor they leave a quieter record, layers of dark, organic, rich mud, where the normal burrowing animals disappear or dwindle, and the microfossil community shifts to species that tolerate low oxygen. Stack enough of those seasons together, and you get a clear stratigraphic message. Something flooded this system with nutrients, repeatedly, over decades to centuries. In deep time that looks like thin bands of blackish sediment, rich in organic carbon, and showing altered nitrogen and phosphorus chemistry compared to the layers above and below. Nitrogen is only half the story. Phosphorus is the other half of the fertilizer twin. Unlike nitrogen, phosphorus doesn't have a big gaseous reservoir. It's mostly tied up in rocks, minerals, and bones. Over geological timescales, it moves slowly. Weathering releases it from uplifted rocks. Rivers carry it to the ocean. Organisms incorporate it into their tissues. And eventually it gets buried in sediments. Humans short-circuited that leisurely loop. To feed crops, we mine phosphate deposits, concentrated layers of phosphorus-rich minerals, often formed in ancient upwelling zones, or from the accumulation of fish bones and guano. Then we grind those rocks up and scatter them over agricultural land all over the world. From an Earth system viewpoint, that is a strange thing to do. We're taking phosphorus that had been sequestered in specific geological provinces and redistributing it onto every continent's soils, into waterways, and eventually back toward the ocean again. But in a massive, sudden pulse. In sediments, you'd expect to see this as a spike in phosphorus content in younger layers, sometimes tied to iron and organic matter, and often coinciding with the same eutrophication signals driven by nitrogen. It's like opening a valve that was previously only dripping. For a relatively brief interval, the planet experiences a phosphorus flood. Then there's the dirt itself. Feeding billions of people hasn't just meant fertilizing fields. It has meant clearing forests, draining wetlands, ploughing prairies, and carving terraces into hillsides. Land use change on that scale strips away vegetation cover and exposes soil to wind and water. The result is erosion, lots of it. River basins around the world show an Anthropocene surge in sediment delivery. Cores from deltas and lakes include thick layers of silt and sand deposited far faster than before, full of pollen from crop plants and weeds rather than native vegetation. In mountain ranges, colluvial fans and alluvial plains record sudden pulses of material arriving downslope. From deep time that would look like this. Over a relatively short interval, many of the world's river systems start dumping more sediment. Basins infill faster, grain size shifts. The mineralogy and organic content change as formerly stable soils are mobilized and washed away. That global synchronization is unusual. It hints at a common driver operating on land nearly everywhere at once. Add these pieces together and you get the outline of a fertilizer Earth signal package. You'd look for a globally distributed horizon where nitrogen isotopes shift in a way consistent with massive new inputs of fixed nitrogen. You'd see phosphorus concentrations rise in many sedimentary settings at the same time, along with signs of nutrient-driven oxygen loss in lakes and coastal oceans. You'd notice an uptick in terrigenous sediment, eroded land, arriving in basins worldwide, often with changed pollen and microfossil assemblages, suggesting rapid land clearance and the spread of a few favoured plant species. To a future geologist tracing cores from multiple continents, that combination would scream, someone was growing a lot of food very fast. But the Silurian hypothesis forces us to ask an uncomfortable follow-up: is this inevitable? Or is it just how our particular civilization chose to feed itself? Imagine a technological society that developed advanced hydroponics, vertical farming, or closed-loop nutrient recycling early on. They might grow much of their food in controlled environments, capturing and reusing nitrogen and phosphorus rather than flushing them into rivers. They might rely on precision agriculture with minimal runoff, or on protein sources that demand far less fertilizer. They might spread more slowly, or accept lower population densities rather than pushing every ecosystem to its productive limit. In that world, the global nitrogen and phosphorus perturbation could be much smaller. Maybe you'd still see local eutrophication around certain river mouths, but not a worldwide pattern. Sediment pulses from erosion might be muted if forests weren't cleared on such an enormous scale for pasture and grain. The biosphere would still be altered, but its chemical and physical scars might blend more easily into the background of natural variability. That's the recurring theme. Even with something as basic as food, the planet doesn't dictate a single path. The signatures we're writing into rock reflect our particular mix of technology, culture, and choices. For anyone hunting for ancient civilizations, that makes the game harder. You can't just look for one kind of fertilizer fingerprint and call it done. You have to consider a spectrum of possibilities, from fertilizer Earth as we're creating it now, to quieter, more contained ways of feeding minds and machines. And so the search widens again. If carbon, nitrogen, and phosphorus are one cluster of clues, heavy metals and industrial toxins are another. If someone else built factories long before we did, the periodic table itself might remember. Carbon, nitrogen, phosphorus, those are the big sweeping strokes of a planetary makeover. Heavy metals are the fine print. Elements like lead, mercury, chromium, cadmium, nickel, copper, zinc, they don't rot, they don't evaporate, and they don't spontaneously vanish. They just move. They dissolve, precipitate, bind to clays, get buried, get exhumed, get buried again. Over deep time they shuffle around the planet like pieces on a slow-motion chessboard. That's why geochemists love them, and why, in the context of the Silurian hypothesis, they're so interesting. Think about lead first. For most of Earth's history, lead has been locked up in ores, galena and other minerals, scattered in veins and deposits. Weathering leaks a bit into rivers. Volcanic gases carry some into the atmosphere. It ends up in sediments at low, fairly stable background levels. Then along comes us. We smelt lead for pipes and pigments. We add it to gasoline. We burn coal, which contains trace metals, and blast those into the sky. In ice cores from Greenland and Antarctica, and in lake sediments around the world, there's a clear 20th century bulge in lead concentrations. Not just a little uptick, a sharp global spike synchronized in time, followed by a partial decline after leaded fuel is phased out. The same story appears with other metals. Coal and oil combustion release mercury, which rides the wind, falls out with rain, and sticks to organic matter in sediments. Cities, smelters, and industrial belts leak zinc, copper, and cadmium into rivers. Stainless steel production throws chromium and nickel into the mix. Everywhere we burn, melt, refine, or electroplate, a thin dusting of the periodic table follows. Some of that dust has a very special form, fly ash. When you burn coal in a power plant, you don't just get invisible gases. You get microscopic glassy spheres, tiny, smooth particles rich in silica, aluminum iron, and assorted metals. They're remarkably uniform in size and shape, and they're almost unknown in natural sediments before large-scale industrial combustion. Since the mid-20th century, those spheres have been raining down on lakes, bogs, estuaries, and the open ocean. Under a microscope, they're distinctive. In cores, a sudden appearance and then global spread of these little industrial beads marks the rise of fossil fuel power like a timestamp. Even if every factory, every building, every city is gone, those spheres can survive in mudstone and shale for millions of years. They're like microscopic marbles whispering, someone was burning a lot of carbon very quickly. But metals and ash don't just arrive from the sky. Civilization also moves elements sideways, in ways that look very odd from a geological viewpoint. Mining is the big one. Ore deposits form where geology has patiently concentrated metals over immense spans of time, hydrothermal veins, magmatic intrusions, sedimentary basins. They're usually localized. Then an industrial species shows up, digs enormous holes, and hauls those concentrated metals somewhere else. Lead, copper, and gold from mountain belts get shipped to coastal cities. Rare elements from a handful of deposits like the platinum group or the rare earths end up scattered in electronics, catalysts, and specialized alloys all over the planet. Eventually, those objects corrode, are discarded, and get buried in landfills, floodplains, and seabeds far from the original ore source. To a future geochemist, that might look like this: strange little islands of metal enrichment in places that make no tectonic sense. A delta plane thousands of kilometers from any known ore body suddenly showing spiky concentrations of platinum, palladium, or neodymium in a narrow stratigraphic band. From an Earth system perspective, that's weird behavior. Nature typically moves elements along gradients, downhill, downstream, from high temperature to low. Industrial mining yanks them sideways, across those gradients, and dumps them in new settings wholesale. Of course, nature isn't chemically innocent. Volcanoes belch metals into the atmosphere. Hydrothermal vents spew out plumes rich in iron, manganese, copper, and zinc, building up chimneys and crusts. Weathering of ultramafic rocks can flood local environments with nickel and chromium. Dust storms ferry iron across oceans. If you look at any sediment core, you'll see metal fluctuations. You'll see spikes tied to a big volcanic province, or to a change in ocean circulation, or to the emergence of a mountain range. So, how do you tell natural noise from an artificial signal? You don't look for one element, you look for patterns. An industrial civilization is likely to leave a particular mix of metals, in particular ratios appearing almost simultaneously around much of the planet. For us, that looks like a mid-20th century layer where lead, mercury, zinc, copper, cadmium and others all jump together, often coincident with fly ash spheres, artificial nitrogen signatures, plastic fragments, and a radiocarbon anomaly from nuclear testing. Natural processes usually don't do that. A volcanic event might spike mercury and sulfur, but not platinum group metals in urban proportions. A hydrothermal system might enrich copper and zinc locally, but not synchronize chromium, lead and cadmium in lakes on every continent within a few human lifetimes. Ratios matter too. The relative amounts of, say, lead to scandium or copper to aluminum, or nickel to vanadium can point to specific ore types and smelting histories. Industrial processes fractionate elements in ways that differ from magmatic or hydrothermal sorting. If a future scientist found the same odd metal ratios appearing in thin layers from South America, Africa, Asia, and a mid-ocean basin all at the same age, they'd have to consider a global, non-tectonic cause. Distribution matters. If you see metal enrichment strongest near ancient coastlines and river mouths, tapering off into the deep ocean, and if that pattern ignores plate boundaries and volcanic arcs but tracks where large populations could plausibly have lived, that starts to look like infrastructure and trade, not just magma and rain. It's that combination, global synchronicity, unusual element ratios and a spatial pattern keyed to landscapes rather than lava flows, that would make the periodic table feel engineered. Would another civilization choose the same metals? Maybe not. They might favor different alloys, burn different fuels, or harness energy in ways that produce subtler chemical traces. But as long as they mined, refined, and moved elements in bulk, some part of the periodic table would likely record their passing. And that's the broader point. Even if bones and buildings vanish, chemistry remembers. The rock record becomes a layered logbook of who grabbed which elements, from where, and dumped them en masse somewhere else. Beyond metals and ash, though, there's something stranger still, materials that never existed on this planet before we made them. Chains of carbon and fluorine, long polymer ropes, exotic compounds tuned for performance, not biodegradability. If metals are the fine print, those synthetics are the highlighter ink. The question is, in 100 million years, would any of that ink still be visible? To answer that, we need one more concept, the technofossil. Think of it as any physical object or material that simply would not exist without technology. Not just a slightly unusual rock, but something whose structure, composition, or shape screams, an engineer made this. Microchips. Aluminum beverage cans. Ceramic insulators with perfect symmetry. Certain kinds of glass. Synthetic polymers like nylon, PVC, polyethylene. Even those tiny coal fly ash spheres we mentioned can be called technofossils because they're a byproduct of a very specific industrial process. But not all technofossils are equal in the eyes of deep time. A steel girder rusts, a copper wire corrodes. An aluminum can might last a few centuries if you're lucky, but given a few million years of groundwater, pressure and heat, it will probably be reduced to a thin smudge of metal oxides in the sediment. Plastics and exotic organics sit in a strange middle ground. They're fragile at the surface, but in the right setting. Parts of them might linger far longer than you'd expect. Start with plastics, in air and sunlight. Most common plastics are not immortal at all. UV radiation, oxygen, and mechanical stress break long polymer chains into shorter fragments. A bottle left on a beach doesn't simply sit there for 10,000 years. It cracks, flakes, turns chalky, and slowly shreds into microplastics, and then nanoplastics. Those microscopic fragments are already everywhere, in deep sea sediments, Arctic ice, mountain snow, river mud. They get mixed with organic matter trapped in clays, carried into estuaries and out onto continental shelves. Over time, some of those tiny particles get buried. Once they're a few meters down in mud, away from light and oxygen, the breakdown slows dramatically. Bacteria might chew on parts of them, but many plastics are resistant to enzymes. Some fraction, perhaps a small one, but still enormous in absolute numbers, could end up entombed in future shale or siltstone. What survives then is not a recognizable fork or shopping bag, but a diffuse, anomalous signal, elevated concentrations of synthetic polymer fragments, maybe altered chemically, maybe cross-linked, maybe partially carbonized, but still weird. A future geologist taking a thin section of that rock could in principle find tiny rounded grains and filaments made of non-natural polymers, or at least their chemical ghosts. They might not see plastic the way we do. They might see unusual carbon-rich microphases with odd additives, titanium dioxide pigments, brominated flame retardants, strange chlorine or nitrogen signatures. Some plastics might go a step further and leave no polymer at all, but still betray their presence indirectly. When plastics char or burn in low oxygen settings, they can contribute to distinct types of soot and organic residues. Those residues can have characteristic ratios of carbon and hydrogen, or distinctive molecular fragments that look nothing like normal plant waxes or algal lipids. So the technofossil record of plastics might be subtle, not a buried landfill neatly preserved, but a thin zone where microplastic-derived organics and additives spike, bound up with clays and ancient river mud. Then there are PFAS and similar forever chemicals. Per- and polyfluoroalkyl substances are built around carbon-fluorine bonds, which are among the strongest in organic chemistry. They don't like to burn, they don't like to break apart, and they don't like to dissolve into harmless pieces. In modern groundwater and sediments, they hang around aggressively, barely degrading on human timescales. But deep time is harsher than any environmental regulation. As sediments get buried, temperatures rise. At a few kilometers depth, rocks can reach hundreds of degrees Celsius. Fluids circulate. Minerals recrystallize. Under those conditions, even very stable organics may eventually be cracked, rearranged, or completely destroyed. Does that mean all PFAS will vanish without a trace? Not necessarily. Their breakdown might not go cleanly to carbon dioxide and fluorite. Intermediate residues could be trapped in mineral lattices, or fluorine might be sequestered in unusual ways. Certain halogenated organics can leave behind distinctive halogen patterns or mineral inclusions that are hard to explain with purely natural sources. And PFAS are just one family. There are also PCBs, dioxins, synthetic dyes, pharmaceuticals, complex pesticides. Each has its own stability curve, its own favourite burial environment. Some could be utterly erased in 10 million years. Others might be transformed but still recognisable to a careful chemist as non-natural, based on their molecular structures or isotope ratios. The environment of burial is crucial. Anoxic basins, places where the bottom waters have little or no oxygen, are already known as excellent preservers of organic matter. Black shales rich in ancient algae, fine laminations that record individual seasons, delicate fossils of soft tissue, these form where decay is slowed to a crawl. If plastic fragments, PFAS or other synthetics rain down into such a basin and get quickly buried by fine sediment, their odds of long-term survival improve dramatically. They're shielded from oxygen, from aggressive microbes, from physical disturbance. Rapid sedimentation helps too. River deltas, turbidite systems on continental slopes, some lake beds, all can bury material surprisingly fast. A century's worth of human trash might end up confined to just a few centimeters of mud, then locked beneath additional layers. In those settings, the technofossil layer becomes thin but powerful, a sharp, concentrated pulse of strange molecules and polymers overlapped with metal anomalies, fly ash, fertilizer nitrogen, perhaps a nuclear signature. Compress it, heat it, metamorphose it a bit, and some part of it could still be legible tens of millions of years from now. But here's the uncomfortable flip side. Most of Earth's surface is not an ideal archive. Ocean crust gets recycled into the mantle, mountains erode. Continents collide, warp, and metamorphose their rocks beyond recognition. Vast stretches of the sedimentary record are missing, either never deposited or later stripped away. From the perspective of, say, 150 million years in the future, our entire technological window might be represented by a handful of surviving basins, a few scattered outcrops, maybe just a couple of centimeters in one or two key cores. If a future civilization samples different places, or if plate tectonics happens to remove the right slices of crust, they could easily miss that thin synthetic seam. And if that's true for us, it would be just as true for any earlier civilization. They might have used completely different materials, biodegradable polymers, ceramics that weather like ordinary clay, organics that break down without a trace. They might have been smaller scale or shorter lived, leaving only local technofossil pockets that never made it into the few enduring parts of the record. So the absence of plastics, PFAS, or other obvious technofossils in ancient rocks doesn't by itself prove no one was ever here before. It just means that so far in the comparatively tiny fraction of Earth's crust we've sampled, we haven't seen a synthetic spike that looks like ours. To move beyond that, we'd need an even sharper signal, something nature almost never does on its own, and that would be hard to erase even by the slow grind of plate tectonics. For that, we turn to the most dramatic technosignature of all, the fingerprints of nuclear fire. Nuclear fire leaves a very different kind of scar. Radioactivity itself is not unusual. The crust is full of naturally radioactive elements, uranium, thorium, potassium-40. Cosmic rays constantly hit the atmosphere and make short-lived isotopes like carbon-14 and beryllium-10. Even supernovae far away seed our solar system with long-lived radioisotopes that slowly decay over billions of years. So just finding radiation in a rock tells you almost nothing. You expect it. What matters is the pattern. Natural radioactivity follows predictable rules. Uranium decays down a chain of daughters at fixed ratios. Thorium does the same. Potassium-40 has a known half-life, and its abundance fits the age of the rock. Cosmic ray-produced isotopes taper off smoothly with depth and time. Artificial nuclear activity scrambles those patterns. Split uranium-235 in a reactor or a bomb, and you don't just get heat. You get a zoo of fission products, isotopes of cesium, strontium, iodine, xenon, tellurium, and many more, in very specific proportions. Some decay quickly and vanish in days or years. Others linger for thousands, even millions of years. You also change the balance of uranium isotopes themselves. Normal natural uranium is about 0.72% U-235. The rest, mostly U-238. Reactors and enrichment processes selectively use and alter those ratios. Reprocessed fuel, waste dumps, and fallout can all leave behind uranium and plutonium isotopic mixtures that simply don't occur in untouched ore. If you were a deep-time geologist, you wouldn't be looking for a vague glow. You'd be looking for an isotopic fingerprint, a thin layer where certain fission products spike together, where uranium and plutonium isotopes look oddly fractionated, where the decay products of now vanished short-lived nuclides appear in impossible combinations. On our planet, we have already created such a layer. Mid-20th century weapons testing threw radioactive debris high into the stratosphere. Fallout from hundreds of atmospheric detonations drifted around the globe, eventually raining out into ice, lakes, soils, and sea floor mud. That left a sharp time marker, the so-called bomb peak. Even now, in sediments and ice cores, you can pick out the early 1960s by the presence of man-made isotopes: cesium-137, plutonium-239, and 240, americium-241. Those don't come from volcanoes, they don't come from cosmic rays. They come from chain reactions triggered on purpose. Nuclear power adds to this, but in a different way. A well-run power plant doesn't spread its fission products globally. It concentrates them on site in spent fuel and reactor components. Catastrophic failures like Chernobyl and Fukushima broadcast contamination over large regions, but not over the entire planet. So, in terms of a clear, planet-wide stratigraphic marker, weapons testing is the heavyweight. It's what produces a nearly synchronous global layer of weird isotopes, thin but unmistakable, like a dotted line in the rock record saying, "Something with advanced physics happened here." The catch is half-life. Many of our favourite tracer isotopes are short-lived on geological scales. Cesium-137 has a half-life of about 30 years. Strontium-90 roughly the same. Even plutonium-241, which decays into americium-241, vanishes on the order of centuries. Give it a few tens of thousands of years, and most of those radioisotopes are effectively gone. Their radiation faded into the background. That doesn't mean the signature disappears completely. Their decay products can still be anomalously enriched. Certain long-lived isotopes like plutonium-244, if ever produced and dispersed in large enough quantities, could remain detectable for hundreds of millions of years. Altered uranium and neodymium isotope ratios from fuel processing and reprocessing might also endure, locked into minerals. But compared to metals or carbon shifts, the nuclear signal is a flashbulb, blindingly bright, then quickly dimming. After a few million years, only the longest-lived components and subtle daughter product patterns would be left to analyze. To understand how subtle but still detectable this might be, it helps to look at one of the strangest natural experiments on Earth, the Oklo reactors in Gabon. About 1.7 billion years ago, groundwater seeped into a rich uranium deposit. Back then, the fraction of U-235 in natural uranium was higher than today because it hadn't had as much time to decay. Under just the right conditions, that water moderated neutrons, and the deposit went critical. It became a natural nuclear reactor, cycling on and off for hundreds of thousands of years. We know this not because we found melted reactor cores, but because the isotopes are wrong. The Oklo rocks have depleted U-235 relative to U-238 in a pattern that matches reactor burn-up. Their fission products, now mostly stable or long-lived daughter isotopes, like certain forms of neodymium and ruthenium, are present in ratios that match controlled chain reactions, not random radioactive decay. In other words, from 1.7 billion years away, geochemists can still read the story of a nuclear reactor, even though it was entirely natural. That's both encouraging and sobering. Encouraging, because it shows that fission signatures, if concentrated and preserved, can survive deep time. Sobering, because it also demonstrates that some nuclear-like signals can arise without any civilization at all. If you found Oklo and didn't know the physics, you might be tempted to invoke technology where none existed. For the Silurian hypothesis, nuclear signatures are a double-edged sword. On one hand, if you ever stumbled on a truly global layer of clearly artificial fission products, unnatural plutonium isotopic ratios, widespread synchronized anomalies in multiple long-lived daughters, decoupled from any known natural uranium deposits that would be as close to a smoking gun as you could hope for, it would be very hard to explain without some kind of technological activity. On the other hand, there's no guarantee that any intelligent species ever goes that route. A civilization might lean heavily on solar, wind, geothermal, or bioengineered energy sources. They might regard fission as too dangerous to touch, or move quickly past it to fusion, or to technologies that leave almost no radiological waste at all. They might be small-scale, low-energy, never building continent-spanning grids or mass-producing bombs. In that case, their nuclear footprint could be negligible. No weapons tests, no massive reactors, no planet-wide fallout. The sharpest technosignature we can imagine simply wouldn't exist for them. So nuclear evidence sits in a peculiar place. It's one of the clearest, most diagnostic signs of a technological civilization, but also one of the least guaranteed to appear. Its strongest tracers fade relatively quickly in geological terms, and its subtler echoes can sometimes be mimicked, at least in part, by rare natural processes like Oklo. If we demand a nuclear smoking gun before we entertain the idea of prior civilizations, we may be setting the bar at a level that even our own society wouldn't clear after a few million years of erosion and decay. To widen the search, we have to step back again from physics and look at something even more fundamental. What we do to landscapes and ecosystems, and whether those changes leave fossils of behavior that no purely natural process would ever quite reproduce. Imagine you're a geologist 10 million years from now, drilling a core through what used to be one of our biggest cities. You're not going to hit a subway tunnel. You're not going to suddenly break into a hollow chamber full of rusted cars and tangled rebar. You're going to hit rock. Maybe oddly mixed, maybe chemically strange, but rock all the same. That's the first uncomfortable lesson here. Physical structures, even the biggest things we build, are fragile on geological timescales. Take maintenance away from a modern city, and it unravels almost immediately. Within months, water gets in everywhere. Freeze-thaw cycles crack concrete. Steel begins to rust and swell, snapping bolts and breaking joints. Glass falls, roofs collapse, plants push roots into every crevice, widening them. Drainage systems clog, streets flood, foundations are undermined. Within a few centuries, in most climates, unmaintained buildings become dangerous ruins. Within a few thousand years, they're not even ruins anymore. They're mounds of rubble and soil, smoothed by erosion, colonized by forests or dunes. Stretch that to millions of years, add changing sea levels, tectonics, glaciations, river systems nibbling away at everything. And the odds that anything still looks like a building drop essentially to zero. To make it into the deep record at all, your city has to get buried. That means sediment has to pile on top of it, fast enough to outpace erosion. Floodplains silt, landslides, volcanic ash, coastal mud. Once those layers build up, weight starts doing its slow, relentless work. At a few meters down, you're in compacted soil and rubble. At tens to hundreds of meters, grains lock tighter, pores close, fluids move and react. Concrete hydrates more, rebar oxidizes and disappears. Voids collapse, roofs and tunnels are crushed flat. What used to be empty space becomes laminated packages of broken material. With more burial and more time, you drift into metamorphism. Temperatures rise, pressures climb, minerals recrystallize. Cements dissolve and reprecipitate. Individual bricks, tiles and slabs lose their identity. What's left is an odd composite rock, angular fragments, glassy bits, rust-stained grains, all welded together. From a distance, under a microscope, that's just another breccia, another conglomerate, another layer among billions. There's also a strong preservation bias in where we tend to build. Coasts are attractive. Trade, transport, food. Many of our largest cities sit on river deltas, estuaries, low-lying coastal plains. Those are dynamic, unstable environments. Rivers change course, storms and tsunamis scour the shore, sea levels rise and fall with climate, and with the slow breathing of ice sheets. Some coastal cities will indeed be buried in thick stacks of mud and sand. Then subsiding basins might protect those layers for tens of millions of years. Others will simply be eroded off the edge of the continent, dragged down subduction zones, recycled into magma. Inland settlements face a different problem: exposure. A city on a plateau or stable craton might avoid subduction, but it sits where wind, rain, frost, and, eventually, glaciers can strip it down grain by grain. Over long enough spans, entire kilometres of rock can be removed from the surface of a continent. Your skyscrapers, your highways, your foundations vanish with the upper layers of the crust they're built on. So, paradoxically, the places we concentrate people are often the worst possible places to preserve architecture. But even if the buildings go, the landscape they sat in may not go back to natural. Think about the scale of the holes we dig and the material we move. Open-pit mines carve out amphitheatres miles across and hundreds of metres deep. We remove entire hillsides, slice through ridges, strip soils. We pile the waste rock somewhere else in vast artificial hills. Quarries leave sheer faces and odd geometries that rivers would not normally sculpt. We also create layers that never existed before. Artificial fill made of crushed rock, brick fragments, concrete chunks, slag, and trash. Whole river valleys are levelled and raised with this material before being built over again. Ports backfill wetlands. Airports rest on compacted imported sediments. Concrete itself is a peculiar rock. Its chemistry is not quite like any natural limestone or sandstone. The aggregate we mix into it can come from wildly different sources, mashed together in ways that natural transport processes wouldn't mimic. In cross-section, a deeply buried highway interchange might one day show up as a peculiar band of unusual aggregate clasts set in an odd cement, slicing across older layers at strange angles. Over deep time, cities dissolve into what some geologists already call urban strata or technogenic deposits, jumbled mixes of anthropogenic material, weird chemical signatures, and disturbed bedding. No recognizable buildings, but a persistent, texturally and chemically distinctive layer. If another civilization existed millions of years before us, its own structures would follow the same rules. Their skyscrapers, their bridges, their monuments would crumble, collapse, and be chewed into grain size. Their tunnels and basements would cave in, their coastlines would shift, their mountain towns would erode. What might endure are the things we're just beginning to recognize in our own footprint: anomalous quarries, strange fills, composite rocks that don't fit normal sedimentary stories. And even then, there's one more problem: actually finding any of it. Geology samples almost nothing compared to the size of a continent. We drill a core here, crack open an outcrop there, map a canyon wall and a quarry face. The overwhelming majority of ancient sediments and basement rocks are never seen by human eyes. Even in well-studied regions, we're reading thin, discontinuous cross-sections through an enormously complex 3D history. So even if a pre-human industrial layer existed, it could be thin, localized, and hard to distinguish from the chaos of natural deposits. Maybe it's preserved only in a few small basins that haven't been subducted or eroded. Maybe we've already drilled through one such layer and written it off as odd breccia with unusual clasts. The Silurian Hypothesis has to live with this needle in a continent problem. It's not that technogenic rock would be impossible to form. It's that, once formed, it could be overwhelmed by everything else Earth does to its surface, then undersampled by the tiny, patchy ways we explore the deep past. To move beyond concrete and quarries, we need to look for signals that can spread further than a single city, and survive longer than any building ever will: changes in biology, in species distributions, in the behavior of the biosphere itself. Biology remembers things that rocks forget. Even if every building is gone, every engine is dust, evolution keeps a kind of ledger. It records who thrived, who vanished, who hitched a ride on whose success. One of the strangest entries in that ledger is domestication. From an evolutionary point of view, a domesticated species is an animal or plant that has suddenly found a cheat code. It stops being shaped mostly by predators, climate, and random disaster, and starts being shaped by us. Look at wheat, maize, or rice. In a few thousand years they go from wild grasses in narrow ecological niches to global superstars. Their seeds get bigger, their husks thinner. Traits that would be suicidal in the wild, like not dropping seeds easily, become advantageous because humans harvest and replant them. The same with animals. Wolves turn into dogs with floppy ears, curly tails, and neotenous faces. Cattle, pigs, chickens all show rapid directional change. Body size, horn shape, coat colour, reproductive timing. These shifts happen far faster than typical background evolution. On a geologic timescale, that kind of rapid, coordinated change across multiple species is weird. If you're sifting through fossils or ancient environmental DNA, and you see a cluster of unrelated organisms all showing sudden, parallel domestication-style traits, that's a huge red flag. Something is doing long-term artificial selection. Something is running breeding programs, and domestication doesn't just tweak bodies. It redraws maps. Our crops and livestock are global migrants. Maize, which evolved in Mesoamerica, is now at home in Asia and Europe. Cattle of Near Eastern origin graze in South America and Australia. Chickens from Southeast Asia are everywhere. From the point of view of future geologists, that's a biosphere suddenly mixing its deck. Species that should be confined to one continent appear in pollen records, bones and DNA, halfway around the world, in synchrony, within a very narrow slice of time. That bleeds into another behavioural fossil, invasives. Natural dispersal tends to be slow and patchy. A plant's range might expand a few kilometres per century as seeds hop from one valley to the next. Animals cross land bridges, island chains, climate corridors. Industrial humans blow that up. We move organisms thousands of kilometres in a single trip. Rats, weeds, mollusks, insects. Some perish, some explode. The pattern this leaves is distinctive. You get sudden first appearances of multiple opportunistic species on distant continents, often in coastal or river-adjacent sediments, all tied to the same narrow stratigraphic window. You also get homogenization. Local floras and faunas lose uniqueness as the same hardy generalists show up everywhere. Paired with this is extinction selectivity. Industrial pressure doesn't just reduce biodiversity randomly. It tends to hit large-bodied animals first, especially those slow to reproduce and living at the top of food webs. Big terrestrial herbivores and carnivores, large marine mammals, apex fish. It also hits habitat specialists, species tied to old-growth forests, pristine coral reefs, undisturbed wetlands. In the fossil record that looks like a sharp pruning of big, specialized forms, while small generalist, disturbance-tolerant species sail through or even increase. You might see rodent diversity holding steady or expanding as large ungulates vanish. You might see hardy, pollution-tolerant shellfish replacing more sensitive species. Again, none of these patterns by themselves prove industry. Climate shocks, volcanism, and sea level swings can also create selective extinction. But industrial stress tends to leave a package: large body bias, specialization bias, plus simultaneous spread of weeds, pests, and commensal species that thrive around civilization. The high-resolution tools for seeing all this are things like pollen records and sedimentary DNA. Pollen grains are tiny, but their walls are made of a tough polymer that can survive tens of thousands, sometimes millions, of years in the right conditions. Layer by layer, lake muds and peat bogs quietly archive what was flowering nearby each season. Drill a core, count the grains, and you see entire landscapes appear and vanish. Forests giving way to grassland, wetlands drying out, sudden booms in a single plant type. In our case, you see abrupt rises in cereal grains, in pasture grasses, in plantation trees like oil palm. You see declines in native forest pollen that don't match natural fire or climate cycles. Ancient DNA, where it survives, pushes that even further. Tiny fragments of genetic material trapped in sediments can be sequenced to identify local plants, animals, even microbes. In some Holocene cores, you can literally watch the arrival of domestic species and their associated microbiomes. For an earlier civilization, something similar could, in principle, be visible. A narrow interval where certain plant lineages suddenly show wider ranges, certain animals appear outside their expected biogeographic homes, and disturbance-tolerant species flourish while specialists fade. A sequence where the ecosystem looks increasingly managed, then stressed, then simplified. But here, the Silurian hypothesis runs into a brutal constraint. Time destroys resolution. Pollen doesn't always preserve. DNA almost never makes it beyond a few 100,000 years, and usually far less, especially in warm, oxygen-rich environments. Older sediments get compacted, mixed, heated. Burrowing organisms churn layers. Rivers cut and rework deposits. By the time you're looking back tens of millions, let alone hundreds of millions of years, the biosphere's paper trail is spotty at best. You can still see big shifts in which species exist, in broad vegetation types, in body size distributions. You can detect major invasions like land plants entering new continents. But the fine year-to-year, century-to-century record that makes human impacts so clear in the Holocene is mostly gone. So we're left with a frustrating situation. Behaviour does fossilise in a way. Through domesticated bodies, invasive ranges, selective extinctions, and the microscopic dust of pollen and DNA. For our own time slice, those traces are vivid. For any hypothetical deep-time civilization, we'd be looking for the same kinds of patterns, smeared, thinned, and partially overwritten. Finding something like that wouldn't end the debate. It would start it, because before we can claim industry in the fossil record, we have to ask a harder question. How long would any unambiguous signature of our own civilization actually last? To answer that, we have to do something slightly unnerving. We have to imagine that we are gone, not just cities abandoned, not just population collapse, completely gone. No one left to maintain roads, dams, satellites, data centers. No one to complain when the power finally flickers out. Then we let the tape run. 10,000 years tick by. That's longer than all of recorded history so far. On continents, the transformation is brutal but familiar. Buildings collapse, steel rusts then vanishes, bridges fall into rivers that have changed course, forests reclaim suburbs, deserts eat highways. The tallest skyscrapers become weird, eroded mounds of concrete and rebar, then just concrete, then just gravel in the soil. Archaeologically, though, this is easy mode. 10,000 years is nothing to geology. Buried basements, subway tunnels, landfills, dams, canals, mine workings, they're all still there somewhere under vegetation and sediment. Ceramics and glass persist. Bronze, stainless steels, and some alloys survive as heavily corroded lumps. Plastics are degraded, but fragments and microplastics linger in soils and sediments. In cave entrances, deserts, dry valleys, whole buildings could survive as recognizable ruins, now stretched to 1 million years. That's roughly the time between early Homo erectus and us. At this point, almost everything on the surface of continents is gone. Erosion has chewed down most mountain ranges by tens or hundreds of meters. Ice ages have come and gone. Rivers have shifted again and again. Coastlines have moved as sea level rose and fell. What's left of us has to be either deeply buried or geochemically stubborn. Cities built on coastal plains, many have been drowned, buried under layers of marine mud and sand, or scraped away by regressions and new river systems. Landfills and industrial sites get compacted into odd sedimentary lenses. Mines and tunnels are collapsed voids, infilled with younger sediments. But the global signals are still clear. Our carbon pulse is locked into the isotopes. The sudden shift in carbon-13 to carbon-12 ratios from burning fossil fuels doesn't require objects, just molecules. The spike in nitrogen from fertilizers, the phosphorus redistribution from agriculture, the weird sulfur and lead signatures from industry, those are baked into ocean sediments and some lake beds. Microplastics and industrial particles are more uncertain. Some will be degraded to their constituent monomers or completely oxidized. Others may become part of strange new mineral aggregates, technofossils, plastic clay composites, metallic spherules from combustion, fly ash glass. They might not scream shopping bag, but they would whisper something was doing chemistry here, pushed to 100 million years. Now we're in deep time. Dinosaurs had already been gone for tens of millions of years by this point in the past. Plate tectonics has done serious work. Whole ocean basins have opened and closed. Most of the oceanic crust that existed in our time has been subducted into the mantle. Continents have reorganized into new supercontinents, rifted apart again, maybe collided once more. On land, the direct archaeological record of our civilization is almost certainly obliterated. Continents lose and remake their surface in cycles. Uplift exposes old rocks. Erosion strips sedimentary blankets. Only a tiny fraction of today's sediments will survive as part of the stratigraphic record that far in the future. But the oceans keep better books. Fine-grained sediments on the deep-sea floor, if they escape subduction, can quietly sit there, layer upon layer, turning into shale or limestone. Within those layers, the global chemistry is frozen in place. Carbon isotope anomalies, nitrogen and phosphorus disturbances. Maybe a brief spike in certain heavy metals that we mobilized in bulk, lead, mercury, copper, rare earth elements, platinum group metals from catalytic converters. Some of our technofossils might be thermally altered but still weird. Polymer-derived organics trapped in mineral matrices. Unusual ratios of certain synthetic compounds that do not match any known natural process. Even if their original structures are gone, their breakdown products could cluster in a distinctive pattern. Add to that a sharp, geologically instantaneous extinction and turnover pattern. Large-bodied mammals pruned, specialized fauna hammered, opportunistic generalists surging, invasive lineages suddenly appearing across multiple continents in the same narrow slice. To a future geologist, that package would stand out the way the end Cretaceous stands out to us. But here's the uncomfortable part. Even that package has limits. Plate tectonics is not gentle. Oceanic crust is almost entirely recycled in less than 200 million years. Continental crust lasts longer, but its sedimentary cover is patchy and constantly reworked. Unconformities, gaps in the record where rocks were never deposited or were deposited and later erased, are everywhere. That means the farther back you go beyond about 200 million years, the fewer continuous, high-resolution archives you have. Whole chapters of Earth's surface history are compressed into thin, incomplete stacks of rock. Many environments, especially those best at preserving artifacts like floodplains and coasts, are exactly the ones most frequently destroyed. So which of our markers are most robust in that chaos? Stable isotope shifts, especially in carbon, oxygen and nitrogen. Elemental anomalies in globally deposited sediments, metal spikes, odd sulfur chemistry, rare synthetic elements, if any, manage to persist as decay products or mineral inclusions, certain minerals that only form under industrial conditions, high-temperature cements, slag-derived phases, concrete-like composites that get metamorphosed but retain odd textures and compositions. All of those are small ripples on the page of deep time, noticeable if you're staring right at the right horizon with the right tools. Easy to miss if your outcrops are poor, your cores are sparse, or that interval simply didn't preserve in your part of the world. Which brings us back to the Silurian Hypothesis. If another civilization had existed for a few 100,000 years with global industry and heavy energy use, it would be hard to hide. You'd expect something like our own planetary fingerprint, a short, sharp chemical anomaly paired with a distinctive biological reshuffling. But if it had been brief, a few thousand years of modest industrial activity, or mostly ocean-based or technologically advanced but low impact in its energy use, the signals shrink. Local perturbations instead of global ones, regional extinctions instead of mass extinctions, subtle isotopic wiggles that could be blurred into the background noise of volcanism, climate cycles and ocean chemistry. Spread that over tens or hundreds of millions of years with most of the rock record missing or mangled, and you get an answer that is both scientifically honest and deeply unsatisfying. Our kind of civilization should leave traces, but there is no guarantee that every civilization would look like ours, or leave a trace large enough, long enough, and lucky enough to intersect the tiny fraction of Earth we've actually sampled. So if we want to look for ancient industry, we have to be clever about when we look. Some windows in Earth's past are more promising than others. So let's lay out the basic ground rules. For something like an industrial civilization to arise, you need a certain kind of planet. Not just any old swamp or lava field will do. You need stable land areas that stick around for tens of millions of years, continents that aren't being constantly drowned or pulverized. You need oxygen levels high enough to support large, active animals and high-energy metabolisms. You need complex ecosystems, food webs with enough redundancy and diversity that some branch of life can afford to experiment with big brains and slow breeding. You also need accessible energy, not just sunlight on the surface, but concentrated stores, thick coal seams from ancient swamps, rich petroleum basins, large metal ore deposits, maybe even long-lived radioactive elements near the surface. A technological species can, in principle, skip fossil fuels and go straight to renewables or nuclear. But the Silurian hypothesis is mostly about civilizations that look enough like us that they change the planet's chemistry. That kind of large-scale industry usually feeds on dense energy sources. Put simply, dry land, breathable air, complex life, and something to burn. Those conditions have not existed uniformly across Earth history. For the first couple of billion years you can basically rule it out. No oxygen for most of that time. No land plants, no complex animals. Even once oxygen rises, the continents are still mostly barren, just rock and microbial films. Complex land-based ecosystems, forests, soils, intricate food webs only really take off in the late Paleozoic, after plants colonize land and build true soils and coal swamps. That's when you first get something that looks like a world where a technological species could exist. So why aren't we focusing all our suspicion on the deep Paleozoic? Because of a brutally practical reason, the rock record. The last few million years, geologically speaking, are a dream for anyone trying to detect a civilization. We have huge stretches of relatively undeformed sediments on continents, lake beds, river terraces, thick, continuous marine sequences sitting on continental margins. We can drill them, date them, cross-check them against ice cores and cave deposits. If there had been something like us in, say, the Pliocene, leaving a global chemical mess, we'd have a reasonable shot at noticing. Go back to the age of dinosaurs or earlier, and the odds start to slide. Older rocks are rare, not because they never existed, but because most of them have been subducted, eroded, or baked. The sediments that do survive from, say, 300 or 400 million years ago are often the lucky fragments. Mountain belt remnants, tilted slices in deeply eroded basins, bits caught in the cores of continents. They've been squeezed, fractured, reheated. Original textures are blurred. Fine chemical details can be reset. Metamorphism is like taking a hard drive and running it through a heat gun. The basic structure might still be there, but a lot of the nuanced data, subtle isotope anomalies, delicate mineral associations get scrambled or erased. On top of that, entire environments are preferentially missing. Low-lying coastal plains, deltas, wetlands, exactly the kind of places where a shoreline civilization would likely cluster, are the most ephemeral. When sea level rises, they drown and become part of the shallow marine shelf. When it falls, they're cut up by rivers and removed. Over deep time, those marginal zones are the least likely to be preserved as thick, continuous, easily readable rock packages. And the layout of continents and seas matters. When continents are mostly clustered into a supercontinent, with vast interior deserts and narrow, storm-battered coasts, preservation of fine, quietly deposited sediments is limited. When sea levels are high and shallow epicontinental seas flood the continents, you can get beautiful, layered marine archives, but often far from land where most industrial activity would sit. If a pre-human civilization was mostly coastal, like ours, then its best evidence might be trapped in sedimentary wedges along ancient continental margins, places that are now buried deep, or have long since been subducted with their oceanic crust. So if you're designing a search strategy, you look for windows where several things line up at once. Times when there were complex terrestrial ecosystems and high oxygen. Times when plate configurations and sea levels favoured widespread, well-preserved marine sediments near continents. Times not so distant that every scrap of rock has been metamorphosed, but not so recent that we already know the story in detail. Those windows exist. Geologists have already identified several intervals in the last few 100 million years that show abrupt warming, weird carbon isotope excursions, and biological turnover, events that, at a very coarse resolution, rhyme with what our own industrial age is doing. In the next sections, we'll walk through some of those suspects. The Paleocene-Eocene thermal maximum and its kin, brief, intense greenhouse spikes that look uncannily like a carbon binge. The Great Ocean Anoxic events, when the seas went sluggish and black shales formed worldwide. Mass extinctions and near misses that reshaped life in sharp, geologically instantaneous pulses, all perfectly explainable by natural processes. But also, if you were looking for civilization like fingerprints in deep time, exactly the sort of chapters you'd read twice. Let's start with the star of the show, the Paleocene-Eocene thermal maximum, or PETM. Roll the clock back about 56 million years. Dinosaurs are long gone. Mammals are diversifying, forests reach into polar latitudes, and the world is already warmer than today. Then on top of that warmth, something happens in the span of a few tens of thousands of years, a blink, geologically speaking, though still much slower than our current century. Global temperatures jump by roughly 5 to 8 degrees Celsius. The deep ocean warms, the Arctic becomes almost subtropical. Crocodile relatives and palm trees live within the Arctic Circle. We know this because the rocks remember. If you drill into marine sediments that cross the Paleocene-Ocene boundary, you see a very distinctive pattern. There's a thin interval, sometimes only a few tens of centimeters thick, that screams that something went off the rails. First, the carbon. Throughout that layer, the ratio of carbon isotopes shifts abruptly. Specifically, there's a large negative excursion in carbon-13. In human terms, the carbon in the system suddenly looks lighter, more like the carbon locked up in biological material and certain methane reservoirs, and less like the heavier carbon of volcanic gases or inorganic carbonates. The shift is global. You see it in deep sea cores, in shallow marine sections, in soils on land. That tells you this isn't a local swamp burping. It's the whole carbon cycle being hit by a massive pulse of isotopically light carbon. At the same time, oxygen isotope data and other proxies tell you the climate warmed sharply. In the deep ocean, you can track a several degree temperature jump. On land, fossil assemblages show plants and animals marching poleward, tropical lineages reaching into higher latitudes. The oceans change character too. Carbonate shells, the tiny skeletons of plankton, start dissolving more readily. In many cores, there's a horizon where the usual white carbonate-rich ooze gives way to darker clays. That's a sign the ocean became more acidic, at least in some layers, as extra CO2 dissolved into seawater and gnawed away at calcium carbonate. Shallow water ecosystems reorganize. On land, there's evidence for intensified rainfall in some regions, drought in others, pulses of soil erosion. Mammals respond with a burst of evolution and dispersal. Some groups shrink in body size, perhaps an adaptation to heat stress and altered food webs. In terms of broad brushstrokes, it all sounds uncomfortably familiar. A big injection of light carbon, rapid warming, ocean acidification, biotic stress and reorganization. If you were looking for an ancient analogue to industrial carbon emissions, the PETM is the poster child. So what caused it? Here's where things get messy. No single explanation is one uncontested. There's a whole menu of natural suspects, and they may have acted together. One candidate is volcanism. Around this time, the North Atlantic igneous province was active, huge volcanic outpourings as the Atlantic widened between Greenland and Europe. Lava intruding into organic rich sediments could have cooked vast amounts of buried carbon, venting CO2 and methane. The timing is suggestive, and some sections show volcanic ash interbedded with the onset of the event. Another suspect is methane release from the seafloor. Under cold, high-pressure conditions, methane can be trapped in ice-like structures called clathrates. Warm the ocean enough, disturb the slopes enough, and those clathrates can destabilize, belching huge amounts of very light carbon into the water and air. The isotopic signal of such a release looks a lot like what we see at the PETM. Others point to the decomposition of massive peat and soil carbon reservoirs, perhaps triggered by a smaller initial warming. Once temperatures rose a bit, permafrost, like deposits and deep organic rich soils, could have thawed and oxidized, reinforcing the trend. Some models even consider orbital cycles, slow changes in Earth's orbit and tilt that alter how sunlight is distributed, as the match that lit the fuse. Not nearly enough on their own to explain the full warming, but maybe enough to nudge sensitive reservoirs into tipping. You'll notice something about all of these ideas. They rely on processes we know exist: volcanoes, methane hydrates, soil carbon, orbital forcing. None requires a technological species. None invokes machinery or deliberate combustion. And crucially, the PETM lacks many of the side effects you'd expect from an industrial civilization. There's no accompanying spike in synthetic elements or weird alloys. No global layer enriched in manufactured metals like aluminum at parts per million levels. No sudden worldwide appearance of novel polymers or persistent organic pollutants. The biological changes, while dramatic look like responses to climate and chemistry, not to targeted habitat destruction or systematic agriculture. Could an ancient industrial civilization be hiding behind the PETM anyway? To make that case, you'd have to explain why its only clear global signature is carbon, why its other activities left no robust trace in sediments we've sampled from every ocean basin, why there's no discrete horizon of strange particles, no distinctive pattern of heavy metal anomalies, no clear extinction pattern that selectively removes large land animals while sparing most microbes and pests. You'd also have to wrestle with timing. The PETM unfolds over tens of thousands of years. Our industrial pulse, so far, is a few centuries old. From the perspective of radioactive decay and sedimentation, our spike is almost a vertical line. The PETM is a thick smear. Any hypothetical civilization driving it would have had to sustain large-scale carbon emissions at relatively steady levels for a duration far longer than we've existed as a species, let alone as a technological culture. That doesn't make it impossible in some absolute sense. But it does make the industrial cause version less parsimonious than the natural explanations that fit comfortably within known geophysics and geochemistry. And yet, for the Silurian Hypothesis, the PETM is incredibly valuable. Not because it's secret evidence of ancient cities, but because it's a natural experiment in carbon cycle disruption. It shows us what a big, rapid carbon dump looks like in the isotope record. It shows how fast the climate responds, how the oceans acidify, how ecosystems shuffle and adapt. It's a rehearsal. When future geologists, human or otherwise, read the Anthropocene layer, they'll see some of the same broad signatures: a sharp negative carbon isotope excursion, warming, acidification. On top of that, they'll see our technofossils, our metals, our artificial radionuclides. By comparing our signal to events like the PETM and other, smaller hyperthermals that punctuate the early Eocene, we gain a calibration scale. We can ask, how big does a carbon pulse have to be to show up? How sharp does it look? How long do its fingerprints linger in sediments? And once you have that calibration, you can turn it around. You can scan older rocks for similar carbon spikes and ask, with a bit more rigour, whether any of them look suspiciously like us, or whether, so far, every strange warming in Earth's past can be comfortably explained by the unruly, but entirely natural behaviour of a living planet. If the PETM is a story of a fevered planet, ocean anoxic events are what happens when the patient stops breathing. Drop down into the Mesozoic, especially the Jurassic and Cretaceous. Much of the world is warm, sea levels are high, shallow epicontinental seas spread across continents. Life in the oceans is rich and productive, and then, at certain intervals, the system tips into something much darker. Geologists call them OAEs, ocean anoxic events. In plain terms, they're intervals when large parts of the oceans, sometimes whole basins, lose their oxygen. Not just a little seasonal low-oxygen zone near a river mouth, but vast, persistent dead zones stretching for thousands of kilometres. In the rock record, they leave one of the cleanest calling cards you could ask for: black shales. Normally, when plankton die and sink, their organic matter is partly eaten, partly rotted, mostly broken down as it falls through oxygenated water, and lands on a seafloor where worms, microbes and burrowers chew through the sediment. The result is a kind of light-coloured, bioturbated mud. Plenty of mixing, lots of little burrows, relatively low organic carbon content. During an anoxic event, that whole recycling system collapses. Surface waters, loaded with nutrients, produce enormous blooms of plankton. So much organic matter rains down that it strips oxygen from the water as it decomposes. Circulation patterns shift in ways that make it harder for deep waters to be replenished with fresh oxygen. If the system crosses a threshold, large swaths of the deep ocean, and even mid-depth waters become oxygen-poor or completely anoxic. In those conditions, the usual seafloor ecosystems vanish. No worms stirring the mud, no clams filtering the water. Organic matter piles up relatively undisturbed. Iron and sulfur chemistry changes, producing dark minerals. Layer after layer of fine, laminated, organic rich sediment builds up, often with a distinct smell of ancient hydrocarbons when you drill into it today. Those are the black shales. They're so distinctive that entire petroleum systems are built on them. Many of the world's oil and gas reserves trace back to organic, rich shales laid down during Mesozoic OAEs. In a way, these events were giant experiments in burying carbon, locking it away for hundreds of millions of years until we started digging it back up. What drives the oceans into that suffocating state? Again, the suspects are all natural. Many OAEs line up with episodes of large igneous province volcanism, enormous outpourings of basalt, like the ones in the Caribbean, Ontong Java, or the high Arctic. Those eruptions can vent huge amounts of CO2, warming the climate. Warmer water holds less oxygen, and increased rainfall can wash more nutrients off land into the sea, fueling productivity booms. Combine that with changes in ocean circulation as continents shift and seaways open or close, and you have a recipe for widespread oxygen collapse. In some events, you even see traces of toxic hydrogen sulfide production in the deep ocean, a truly hostile environment. The rhythm is familiar: volcanism, CO2, warming, nutrient loading, oxygen loss, ecological disruption. It's not hard to see the uncomfortable parallels to modern trends. Fertilizer runoff feeding coastal dead zones, warming waters exacerbating low oxygen conditions, fisheries shifting as oxygen minimum zones expand. But when you zoom in on the details, OAEs look very different from an industrial footprint. For one thing, timing. Most OAEs unfold over tens to hundreds of thousands of years. Their onset in the rock record is drawn out, not razor sharp. Black shales thickening over meters of sediment isotope shifts that smear across long intervals. Our industrial pulse so far barely occupies a few centimeters in a typical deep-sea core. Then there's the chemistry. OAE black shales do show interesting patterns in elements like molybdenum, uranium, vanadium and sulfur, signals of low oxygen conditions and changing redox chemistry. But they don't show a synchronized global step change in manufactured metals. No spike in leaded gasoline residues, no anomalous aluminum at levels suggesting large-scale smelting, no novel synthetic organic compounds that resist breakdown. Their carbon isotope records show large excursions, but again, those can be matched with volcanic CO2, enhanced weathering, and organic carbon burial. Nitrogen isotopes indicate changes in nutrient cycling, not the abrupt fertilizer-driven footprint you see when humans start fixing atmospheric nitrogen at scale. If you wanted to argue that an OAE was driven, or at least nudged, by a technological species, you'd need more than just black shales and warm water. You'd be looking for discordances, for patterns that don't quite fit the usual volcanic climate story. You might look for a very sharp onset in some cores, a near instantaneous shift in isotopes that outpaces what even the wildest volcanic pulses can deliver. You'd search for unusual combinations of contaminants, trace enrichments of metals that normally don't travel together in natural systems, but do in industrial processes. Platinum group metals paired with rare earth elements in ratios suggestive of catalytic converters or electronics, not mantle plumes. Tiny spherules or particulates with alloy compositions that don't match any known meteorites or igneous rocks. You'd comb the organic fraction of those shales for strange molecules, long-lived synthetic compounds, halogenated organics, polymer fragments, that don't match any known biological pathway, preserved in micropockets shielded from degradation. You'd also watch the biological response. Natural OAEs show particular extinction and survival patterns. Some plankton groups crash, some opportunists flourish. Benthic communities reorganize according to oxygen thresholds. An artificial driver might leave a different signature, perhaps sharper losses in certain size classes, or peculiar survivals that track pollution tolerance more than oxygen levels. So far, when geologists interrogate OAE cores with these questions in mind, the answers point back to a hyperactive but natural Earth, volcanism, shifting seas, runaway feedbacks in nutrient and oxygen cycles. No global layer of technofossils, no chemically impossible alloys, no planetary scale pulse of synthetic molecules. For the Silurian Hypothesis, that's still useful. OAEs tell us what it looks like when the oceans themselves go hypoxic on a grand scale without help from machines. They give us a template, the thickness of black shales, the shape of isotope curves, the element patterns that scream stagnant seas, volcanic CO2, nutrient overload. And with that template in hand, we can turn to the rest of the rock record and ask more confidently, does anything deviate from this script in a way that hints at artifice? Or are even the darkest seas of the past just another chapter in the long, chaotic autobiography of a living planet? If OAEs are the oceans quietly suffocating, mass extinctions are the times when the whole biosphere takes a punch to the face. Paleontologists talk about the big 5 mass extinctions in the last 540 million years. These are the intervals when extinction rates spike so high over such a short geological time that whole branches of the tree of life are chopped off. End Ordovician, late Devonian, end Permian, end Triassic, end Cretaceous. Each has its own flavour and its own leading suspect. The end Ordovician, about 444 million years ago, seems tied to a rapid glaciation and sea level fall, possibly triggered by changes in atmospheric CO2 and continental positions. Shallow seas where most marine life lived retreated. Habitats vanished, then, as ice melted, the seas rose again. A 1-2 punch of climate swing and habitat loss. The late Devonian is messier, more stretched out. It may not even be a single extinction, but a cluster. Rising plants on land changed weathering and nutrient runoff. Anoxic events in the oceans appear again. Reef ecosystems suffer repeated blows. The end, Permian, 252 million years ago, is the darkest chapter. Up to 90% of marine species gone, huge losses on land. The leading explanation, massive Siberian traps volcanism. Enormous CO2 emissions, global warming, acid rain, ocean acidification, widespread anoxia, maybe even eruptions of methane. A cascade of feedbacks that turned the planet briefly into something genuinely hostile to complex life. The end Triassic, around 201 million years ago, lines up with another volcanic monster, the Central Atlantic Magmatic Province. Again, huge basalt flows, CO2, climate whiplash, ocean stress, restructuring of ecosystems. And then the celebrity extinction, the end Cretaceous 66 million years ago. Here we get a rare smoking gun. A big asteroid hits near what is now Chicxulub in Mexico. A global iridium layer, shocked quartz, tiny glass spherules, wildfires, a brief intense impact winter followed by longer-term changes, may be amplified by the Deccan Traps volcanoes in India. So volcanoes and rocks from space, climate swings, sea level changes, anoxic oceans. All natural, all ferocious. Where does an industrial civilization fit into this picture? If you imagine a technological species driving a mass extinction, the end Cretaceous is almost the wrong kind of event. It has that singular, catastrophic spike, the asteroid, with a clean physical trace. There's no need to invent an advanced dinosaur civilization burning fossil fuels when a 10-kilometre rock from space will do. The Permian is where imaginations turn. A drawn-out crisis, CO2 overload, warming, acidification, oxygen loss, strange patterns in carbon and sulfur cycles. From far away in time, a fossil fuel binge and a basalt flood might look superficially similar. Too much greenhouse gas, too fast. But when you look at the details, industrial impacts and big natural triggers leave different ecological fingerprints. Asteroid impacts give you that thin, global layer of impact debris, nickel-rich dust, shocked minerals, impact glass, a sharp break in microfossils right at the boundary. Volcanism tends to smear its effects over longer intervals. You see repeated pulses of environmental stress, stepwise extinctions, chemical signatures that wax and wane with eruptive phases. Industrial impacts, as we know them, are oddly selective. They hit large-bodied vertebrates hard, especially on land, but also pick off particular guilds, top predators, migratory specialists, species tied to old-growth habitats. Pollution pressure can favour hardy generalists over specialists. Overfishing wipes out big, slow-breeding marine animals first. Urbanisation and agriculture fragment landscapes in ways that disadvantage creatures needing vast, contiguous territories. They also come with distinctive chemical baggage, heavy metal anomalies patterned like industrial emissions, abrupt nitrogen isotope shifts from artificial fertilizer, synthetic organics, plastics, radionuclides. Could a civilization cause a mass extinction and somehow dodge all those chemical tells? You could try to imagine one that never burns fossil carbon at scale. Maybe it learns early to run on solar, wind, geothermal, or something stranger. It might still wreck biospheres through habitat destruction, bioengineered organisms, invasive species, intentionally or accidentally spread across the globe. There, the fingerprints might be more biological than chemical. Sudden appearances of cosmopolitan, opportunistic species at the expense of local endemics. A weird reshuffling of food webs where human equivalents and their commensals proliferate, while everything else thins out. But even then, complete chemical invisibility is a high bar. Any complex technology seems to require concentrated energy, mining and materials processing. That means moving metals around, altering landscapes, generating waste heat and byproducts. Even a very green civilization would have to interact with geology and chemistry on some non-trivial scale, especially if it reached global dominance. There's another angle: how life recovers afterward. Natural mass extinctions show characteristic rebound patterns. Diversity crashes, then slowly rises. Surviving lineages radiate into empty niches. Recovery can take millions to tens of millions of years. The end Permian, especially, leaves a long, grim recovery tale. Ecosystems remain simplified for ages, with repeated aftershocks. You also see certain clades doing better than others in ways that match the apparent stressor. After an impact winter, groups able to handle low light and short food chains. Things like detritus feeders and small generalist animals have an edge. After greenhouse extinctions, heat-tolerant and opportunistic species fare better. An engineered extinction might, in theory, show a different kind of selectivity. Perhaps groups associated with pollution tolerance or with close symbiosis to a technological species do unusually well. Maybe recovery is oddly lopsided, with some ecosystems bouncing back quickly, while others remain depressed in ways that don't quite fit climate or sea level stories. But this is where humility has to come in. From tens or hundreds of millions of years away, a lot of different causes blur into similar patterns. Volcanism, methane releases, asteroid impacts, orbital changes, microbial revolutions. They can all drive fast climate shifts, anoxia, acidification, sea level swings. They can all reshape food webs, favour opportunists, and leave long, ragged recovery intervals. The big five, as far as we can tell, are well explained by a hyperactive Earth and the occasional cosmic sucker punch. Their selectivity, who lives, who dies, who thrives afterward, fits the physics, chemistry, and ecology of those drivers without needing a hidden industrial hand. That doesn't prove no such civilization ever existed. It just means that, so far, nothing in the mass extinction record screams design over disaster. The patterns we see could, in principle, cloak an artificial trigger, but they don't require one. In other words, the rock record keeps telling the same story. A restless planet, a fragile biosphere, and a history of near apocalypses that look, at our current level of resolution, like natural experiments rather than engineered catastrophes. If the extinction record doesn't obviously demand an earlier industrial civilization, the next question is more basic. How likely is a civilization like ours in the first place? Not in a cosmic sense, just here, on this one restless planet. Evolution is full of surprises, but it also has habits. Biologists call it convergent evolution, the tendency for similar solutions to evolve independently when life faces similar problems. Wings evolved in insects, pterosaurs, birds, bats. Eyes evolved over and over in jellyfish, mollusks, vertebrates. Echolocation shows up in bats and toothed whales, complex sociality in ants, termites, naked mole rats, primates. Intelligence, too, seems to be one of those recurring tricks. If you zoom out, big-brained, flexible behaviour has evolved many times. Corvids and parrots among birds, dolphins, killer whales, and some other cetaceans. Octopuses and cuttlefish in the oceans. Certain primates, of course. Even some insects show surprising cognitive sophistication in miniature. You get planning, problem-solving, memory, social learning, even what looks suspiciously like play and creativity, over and over again in lineages that diverged hundreds of millions of years ago. So, from that angle, intelligence is not a one-off miracle. It's something evolution stumbles into whenever there's an advantage to being able to model the world and change your behaviour quickly. But there's a catch. Most of that intelligence lives in bodies and environments that don't easily point toward industry. Take birds. Ravens can solve multi-step puzzles. New Caledonian crows make and modify tools, passing techniques down through generations. Parrots learn words, understand categories, sometimes grasp simple numbers. Their brains are tiny but densely wired, packing primate-level cognition into a few grams. Yet birds are mostly small, warm-blooded flyers or climbers. They manipulate the world with beaks and feet, not five-fingered hands. They build nests, stash food, sometimes use sticks or cactus spines. But the leap from twig tools to blast furnaces is enormous, and the bird body plan is not optimized for hauling logs, digging mines, or spending hours tending an open fire. In the sea, dolphins and whales rival apes in social complexity. They have long childhoods, intricate vocal cultures, coordinated hunting strategies that vary from pod to pod like regional traditions. Some researchers argue that sperm whales and orcas have a kind of clan-level identity passed down through generations. But water is a terrible place for industry as we know it. You can't easily smelt metal underwater. You can't light a stable fire. Chemical energy sources exist, hydrothermal vents for instance, but they're patchy, dangerous and hard to harness without already having technology. Cephalopods might be the strangest case. Octopuses solve mazes, open jars, use coconut shells as portable shelters, learn by watching. Their nervous systems are so different from ours that each arm has its own mini-control center. They're intelligent, but their bodies are soft, short-lived, and solitary. No hands, no long-term social structures, no long lifespan to accumulate culture over decades. Intelligence, in all these cases, has clearly been favoured by evolution. But it expresses itself in ways that fit the body and the niche: stealthy reef raids, clever foraging, complex social games, not smokestacks and satellites. That's where the distinction matters: tool use versus an industrial civilization. Plenty of animals use tools, some shape them. Chimpanzees strip leaves from sticks to fish for termites. Sea otters use rocks as hammers. Crows bend wires into hooks. These behaviours can be taught, improved, even passed down. What almost never appears outside humans is cumulative technological culture, the kind where each generation starts a little further ahead because of what the last one built. Industry, the kind the Silurian Hypothesis worries about, needs that cumulative ratchet. You don't just have tools, you have traditions of improving tools. You don't just have knowledge, you have systems for storing, copying and scaling it. And you need something else that evolution doesn't hand out automatically: access to high-quality energy and materials in a form you can actually use. Fire is the big one. To get an industrial civilization anything like ours, you probably need controlled combustion on land. Fire lets you cook food, freeing up energy and time. It lets you harden wood, fire ceramics, eventually smelt metals. It becomes a general-purpose technology: heat, light, defense, landscape management. But to use fire, you need dry fuels, oxygen-rich air, and a body plan that can manage getting close to flames without constantly dying. You need hands that can carry burning branches, minds that can understand cause and effect well enough not to burn the forest down every single time. Marine mammals are out by default. So are most forest floor animals that don't have the ability to manipulate objects delicately at arm's length. Metallurgy is another bottleneck. Even if some clever species figured out to use simple tools and maybe even fire, you need accessible ores near the surface, and a reason to experiment with them. You need to be able to gather enough people, resources and time to run those experiments generation after generation. That implies not just intelligence, but surplus. Agriculture or something like it, or at least extremely efficient foraging. Stable social groups large enough to support specialists who aren't just getting their next meal. When you stack all these constraints, body plan, habitat, lifespan, energy sources, materials, social structure, it becomes clearer why, on Earth, full-blown industry has appeared exactly once that we know of. Not because intelligence is rare, but because the specific path from flexible brains to fossil fuel burning, metal bending, planet reshaping civilization runs through a very narrow set of conditions. So where does that leave the idea of pre-human civilizations? From an evolutionary perspective, it's not impossible that something pre-human became clever, social, and tool-using. Dinosaurs produced large-brained forms. Some marine reptiles had decent encephalization. Certain ancient birds and mammals clearly experimented with complexity. But intelligence without industry is entirely normal. Intelligence with industry might require such a precise alignment of traits and environments that it's unsurprising we only see one case in 500 million years of complex life. That's why scientists keep a cautious framing. Biology tells us that brains, problem-solving, even culture are not unique to us. Convergence suggests that, given enough time, evolution does tend to explore those options. But nothing in the record so far forces us to conclude that industrial civilizations are an expected outcome rather than a quirky accident. Plausible in principle? Yes. Supported by evidence in deep time? Not yet, which in a way only sharpens the Silurian question. If such a civilization did arise long before us, how would we even know? What exactly should we be looking for in the rocks? That's where the search methods come in. If you're a geologist taking the Silurian hypothesis seriously, even just as a thought experiment, you don't start with pyramids under the sea or blurry satellite photos. You start with mud, more specifically, long, perfect cylinders of layered mud, sand, and tiny shells pulled up from deep below the seafloor or the bottom of ancient lakes. Cores. Coring is how we read Earth's diary without ripping out the pages. You drop a hollow tube into the sediment, drive it down through the layers, and pull up a vertical timeline. The top is young, the bottom is old. Between them, every millimetre is a slice of vanished worlds. Once you have that cylindrical time machine, the toolkit looks surprisingly modest. Stratigraphy, to figure out what layer came when and how fast it piled up. Geochemical assays, to measure the exact ratios of elements and isotopes. Microscopy, to see what tiny fossils, crystals and grains are doing at each depth. Sometimes X-rays or CT scans, to see structure without slicing the core apart. It's quiet, finicky work, but it's the kind of work that could in principle catch a civilization that burned through a planet and disappeared. The first question is where to look. Continents are terrible libraries. They crash together, split, erode, get scraped by glaciers, cooked by magma. Mountains rise and vanish. Anything sitting on the surface has the geological life expectancy of a mayfly. So you go to the places that change slowly, old stable parts of the ocean floor where fine sediment has been raining down for tens of millions of years with almost metronomic regularity. There, a few centimetres of mud might represent thousands of years, stacked up like pages in a book that's hard to tear. You also target rapid burial environments, river deltas where floods dump huge loads of silt in a hurry, submarine fans at the base of continental slopes, anoxic basins, deep, poorly ventilated pockets where the bottom waters run out of oxygen and dead things fall in, then don't rot properly. Those places are the hoarders of the geological world. They keep everything. Lakes are another favourite. A deep, quiet lake that's persisted for hundreds of thousands of years can build up a layered archive of pollen, ash, chemicals and microfossils. Each year might leave a couple of distinct bands like tree rings, light summer sediment, dark winter organic matter. If something weird happened, the lake notices. So suppose you pull up a core from one of these good archives and go hunting for Silurian signatures. What would it take for scientists to start whispering to each other in the hallway? It wouldn't be a single oddity. Earth can fake almost any one signal. Carbon isotope spikes from volcanoes and methane burps. Heavy metal enrichments from unusual rocks or long-dead hydrothermal vents. Plastic-like polymers from natural resins and weird organic chemistry. Oxygen crashes from natural ocean stagnation. To even start thinking about an industrial cause, you'd need a stack of anomalies all lining up in the same slice of time. Maybe you see a sharp, rapid negative carbon isotope excursion, the kind of thing you'd expect if enormous amounts of biologically processed carbon got dumped into the atmosphere and ocean very quickly. In exactly the same layers, you see a strange pattern in nitrogen isotopes, suggesting global-scale tinkering with the nitrogen cycle, like what our fertilizers do now. In the same layers you find spikes of certain metals, copper, lead, rare elements that don't usually travel together in those amounts, along with tiny spherules that look suspiciously like industrial fly ash. And threaded through all of that you find unusual, long-chain organic molecules that don't match any known natural polymer, or odd halogenated compounds that shouldn't be there without synthetic chemistry. You'd also want to see biological fallout, shifts in the kinds of plankton fossils, pollen changes on land. A little extinction bump in some groups may be selective for organisms sensitive to temperature or chemistry shifts. Not a dinosaur killer, but something more like the subtle biosphere jolts we're generating now. One core like that would be fascinating, but it wouldn't be enough. Because the planet is noisy, and coincidence is cheap, you design the search so you're not fooling yourself. That means you don't start by staring at cores until you find the weirdest bit and then inventing a story. Instead, you write down your rules in advance. You pre-register your hypothesis the way good clinical trials do. For example, if we're looking for Silurian-style industry, we predict that in any given 5 million year window, truly industrial events will show A, B and C, in this order within this thickness of sediment, and they'll be replicated across at least N different basins on different continents. Then you go out and test that specific claim. You sample multiple sites that cover the same time window. You run the same measurements in the same way. You don't move the goalposts every time you see something intriguing. If one site shows odd carbon but no matching metals, it goes in the interesting, probably natural folder. If another has strange metals but boring isotopes, same story. You only start sweating when sites thousands of kilometers apart all show the same bundled anomalies at the same age. Cross-site replication is the antidote to cherry-picking. It's what turns a good story into a serious candidate explanation. And notice something, all of this remains useful science even if you never find anything you dare call Silurian. Carefully scanning cores for multi-signal anomalies teaches us how natural hyperthermals actually work. It helps disentangle volcanic carbon from methane clathrate releases, asteroid impacts from ocean anoxia, slow background changes from genuine shocks. Refining geochemical techniques to detect faint synthetic-like compounds improves our ability to track modern pollution. Mapping how the nitrogen and phosphorus cycles have changed through deep time helps calibrate how extraordinary our current fertilizer binge really is. Even the discipline of writing down in advance what an industrial civilization would look like in rock forces us to think more clearly about our own. Which of our fingerprints are robust over millions of years? Which vanish quickly? What matters geologically about the Anthropocene and what is just surface noise? If the answer at the end of all that work is probably no ancient industry, then the Silurian hypothesis has done its job anyway. It has made us look harder, measure better, and understand more deeply how a planet remembers and how it forgets. When you start talking about lost civilizations, though, something predictable happens. The science quietly working in cores and isotopes gets drowned out by Atlantis, mystery pyramids, and viral posts about impossible artifacts. So it's worth drawing a very sharp line here. The Silurian hypothesis is a deep time question. It's asking, could an industrial civilization have existed millions of years before us? And if so, what traces would it leave in the rocks? That is a completely different question from, did humans or human-like beings build advanced cities 10,000 or 20,000 years ago and then vanish from history? Those two timelines aren't even in the same universe. Human ancient history is measured in thousands of years. Deep time geology is measured in millions to hundreds of millions. On a geological timescale, the entire span from the first stone temples to your smartphone is a thin scratch, less than a millimeter deep. And here's the key thing. The closer you are to the present, the more evidence survives, and the harder it is for a whole civilization to just disappear without a trace. We have stone tools going back 3 million years. We have footprints, campfires, butchered bones, By the time you get to, say, 20,000 years ago, the record is thick with detail. Campsites, hunting blinds, cave paintings, carved figurines, pollen records of fields being burned and managed. By 10,000 years ago, we can watch agriculture emerge in multiple regions. We can see wheat and barley and rice being domesticated. We have whole Neolithic villages with walls, floors, trash pits, not legends. Excavated, measured, dated. So when someone says, what if there was an advanced global civilization before Egypt and it got wiped out? They're not asking a Silurian question. They're asking us to believe that a dense, complex, worldwide human culture somehow left less evidence than small hunter-gatherer bands did tens of thousands of years earlier. That's backwards. This is where a lot of misinformation sneaks in. It takes real gaps in our knowledge and fills them with stories that don't respect how evidence actually works. Anomalies get treated like trump cards. A structure with unclear purpose becomes impossible. An artifact with a disputed date becomes out of place. A poorly documented excavation from the 1800s gets recycled, stripped of context, and elevated to proof that mainstream science is hiding something. Layers get misread or misrepresented. A piece of pottery found in a disturbed pit is claimed to be millions of years old because the bedrock underneath is that old, even though the pit was dug yesterday. Radiocarbon dates with large error bars are cherry-picked for the oldest possible value and presented as exact. In isolation, each of these things can sound compelling. But science doesn't treat isolated curiosities as final answers. It treats them as questions. Out-of-place objects usually resolve into one of a small handful of options: mislabeling, contamination, mixing of layers, forgery, or a real but misunderstood natural process. And sometimes they do turn into genuine discoveries. A tool type that shows up earlier than we thought. A site that pushes back a migration date. What they don't do, on their own, is overturn everything we know about how civilizations form, grow, and leave traces. That's what people mean when they repeat the phrase, "extraordinary claims require extraordinary evidence." It's not a slogan for shutting down curiosity. It's a reminder that the more a claim asks us to rewrite, the more independent, converging lines of data we should demand. If you want to argue for a global human civilization 50,000 years ago, you don't just need one curious ruin or one puzzling map. You need architecture, tools, mines, quarries, trade goods, trash heaps, skeletons, DNA patterns, changes in plant and animal distributions across continents, across multiple dating methods, all lining up. If you want to argue for a Silurian-style industrial civilization 50 million years ago, you need even more. Stacked geochemical signatures, cross-basin replication, biosphere shifts, exotic compounds that nature doesn't usually make, all in a tight time slice, all pointing in the same direction. Notice that the rule is the same in both cases. What changes is the timescale and the kind of evidence that can possibly survive. So how do you stay open-minded without getting pulled into every dramatic story that scrolls past your feed? One way is to borrow the mindset of the core driller. Be generous with questions, strict with answers. It's completely fair to say, this site is weird, or we don't fully understand how this structure was used, or the timeline here is still being refined. Archaeology and geology are full of active debates and genuine mysteries. But between "we don't know yet" and therefore advanced lost civilization, there are usually dozens of more ordinary explanations that fit better with everything else we've learned. Staying curious doesn't mean lowering the bar for evidence. It means raising your standards as your questions get bigger. If an idea excites you, Atlantis, ancient high technology, Silurian civilizations, you can treat that excitement as a reason to dig deeper, not a reason to stop. Ask, how was this dated? What other experts say the opposite, and why? Does this anomaly show up in multiple places, measured in multiple ways, or is it a one-off? Has the claim changed over time as people point out flaws, or is it frozen in place? The difference between mystery and method isn't that one kills wonder and the other feeds it. It's that method gives mystery a path forward. The Silurian hypothesis lives or dies by that method, by cause, cross-checks, and the willingness to say at the end, we looked as hard as we could, and here is what the planet actually tells us. So after all of this, after drilling our imaginary cores and squinting at isotopes and arguing with Atlanteans in the comments, you might reasonably ask, why does any of this matter? If the answer is probably no, there was no dinosaur version of Dubai, what's the point of the Silurian hypothesis? One answer is uncomfortably simple. It turns the telescope around. Instead of using geology to hunt for some imaginary past civilization, we use the same logic to see our own future footprint. When Frank and Schmidt framed the Silurian hypothesis, they weren't just indulging in sci-fi. They were asking, if we vanish, what parts of our civilization actually last long enough to be seen 50 million years from now? Not in ruins, not as monuments, but as chemistry. We've already talked about some of those signatures. Carbon isotopes pulled out of ancient shells, nitrogen and phosphorus spikes from fertilizer, heavy metal enrichments, weird synthetic compounds that natural processes almost never make. The hypothesis forces us to sort our choices into two piles. On one side, the short-lived noise, things that feel huge to us but barely scratch the rock record. Political systems, brand names, which language you're listening to this in, even most buildings, roads and dams. On the other side, the deep time signals, things that alter global cycles in ways that can't easily be undone. Gigatons of carbon moved from rock to air in a geological instant. Extinction pulses that permanently reshape ecosystems. Long-lived pollutants that don't break down on human timescales. Ask the Silurian question, and you're really asking what, if anything, are we doing that a geologist 50 million years from now could still detect with a drill and a mass spectrometer? That's a harsh test for sustainability. Some things we worry about intensely might not matter to the rocks at all. Some things we barely think about might be among the most permanent acts our species will ever perform. For example, most plastics will break down, but not into nothing. They fragment into microplastics that can get buried in sediments. Some will probably cross-link, get entombed, and become part of future sandstones and shales. A thin, glittering layer of technofossils, fossil fuel CO2 is even more telling. The carbon pulse we're injecting into the atmosphere and oceans right now will echo in climate, ocean acidity, and sediment chemistry for tens to hundreds of thousands of years, even if human societies stabilize emissions soon. On the scale of your life, climate change can feel like a rolling crisis. On the scale of deep time, it looks like the opening spike of a new stratigraphic chapter. Geologists have started calling that chapter the Anthropocene, the slice of Earth history dominated by human activity. It's still a debated term, and not every geologist agrees exactly where to draw the line. But if you apply Silurian logic, you can see the outlines. A sharp isotopic wiggle in carbon, industrial nitrogen and phosphorus reshaping soils and lakes. A sudden appearance of aluminum, concrete, plastics and other novel materials. Changes in pollen as forests are cleared and crops spread. A spike in extinction rates. We are writing that chapter right now, line by line, in mud at the bottom of lakes and dust settling on ice sheets and shells growing in warming seas. The Silurian hypothesis asks, if some other species millions of years from now evolves big brains and drills cores, What will they see when their drill hits the thin layer that used to be us? Will it look like a brief chemical accident? A flash of carbon and plastic and extinctions that came and went? Or will it look like the start of something that persisted and adapted, a civilization that learned to live within planetary limits without erasing its own future in the rock? That's the sustainability question, stripped of slogans. Not is this policy good for the next election, but does this choice echo for 100,000 years? And then there's the part of the Silurian hypothesis that looks up, not down. If industrial activity leaves distinctive planetary fingerprints, then in principle we don't just use this idea on Earth. We can use it on other worlds. SETI, the search for extraterrestrial intelligence, has traditionally focused on listening for radio signals or looking for megastructures. But there's another approach. Look for civilizations the way a geologist would, as anomalies in planetary chemistry, an atmosphere way out of equilibrium, strange combinations of gases that don't match volcanism or simple biology, industrial pollutants on worlds that are otherwise natural, night-side heat patterns that don't match sunlight. This is sometimes called techno-signature work, and the Silurian hypothesis is one of its quiet foundations. To ask, could we detect a Silurian civilization in our own rocks, is very close to asking, could we detect ourselves in the spectrum of a distant planet? If we can't even imagine our own long-term signature clearly, we're not going to be very good at spotting anyone else's. There's also a kind of emotional vertigo that comes with all this. When you spend time thinking in millions of years, our whole era shrinks. Everything you recognize, cities, empires, religions, the entire sweep of written history, collapses into something like a single bright line in a drill core. It's humbling, but it can also be strangely comforting. Because in that view, we're not the grand finale of Earth history. We're one experiment among many in a 4 billion year story, a story that has already seen continents collide, seas vanish, forests rise and burn, creatures appear and disappear. Whether or not there were Silurian-style predecessors, the planet has rolled on. You can hear that as nihilism. Nothing we do matters, because in 50 million years it's all mud. Or you can hear it as permission, precisely because our layer is thin. We have a chance to decide what kind of thin layer it will be. One marked by a sharp extinction, a carbon spike, and an abrupt end. Or one that shows a spike, a wobble, a crisis, and then a long, stable tail where the signals of destruction fade and new, gentler patterns take over. The Silurian hypothesis doesn't answer that for us. It just gives us a way to pose the question with evidence instead of myth. So, as you drift towards sleep, you can let your mind wander. Imagine some distant future intelligence, human or not, brushing dust off a rock and reading the record of our age. What story will they tell from that thin band of altered chemistry? Will they see a civilization that flared and vanished? Or one that learned, just in time, how to live long enough to become a quiet, durable part of deep time? Right now, buried somewhere beneath your feet, that answer is being written. So after all of that, where do we actually land? Not in certainty. Not in a secret chapter of history where reptile engineers built power plants under Triassic stars. We land in a quieter place. The Silurian hypothesis doesn't say there was a civilization before us. It doesn't even say there probably was. It says something much more modest and in some ways more unsettling. If there was, what would we be able to see now? And what would we miss? Detectability is the real heart of it. When you strip away the sci-fi gloss, you're left with a technical question. What kinds of activities rise to the level of geological handwriting, and which ones vanish like footprints in a storm? We've seen that some signals are strong candidates. Carbon isotopes, for one, A huge, rapid release of fossil carbon would tweak the ratio of light to heavy carbon in shells, inorganic matter, in carbonate rocks, that wiggle can survive for tens of millions of years. We found similar wiggles from past hyperthermals like the PETM. They show that large carbon pulses happen even without factories or power grids. Heavy metals and industrial pollutants are another. If a civilization mined and scattered unusual amounts of lead, mercury, copper, or rare metals, that enrichment could get locked into sediments. It wouldn't paint the whole planet evenly, but in the right basins it could look like a distinct chemical scar. Our own leaded gasoline era, our coal burning, our mining tailings are already starting to do that. Then there's the zoo of synthetic residues, plastics that don't exist in nature. PFAS and other fluorinated chemicals, complex organic molecules that only appear when a chemistry lab or a factory has been at work. Some of these will break down. Some will turn into simpler compounds. But a fraction may end up trapped in clays, in lake bottoms, in ocean mud, where cold, darkness and burial slow the clock almost to zero. Taken together, isotopes, metals and technofossils are the most likely fingerprints any industrial species would leave. And yet, each of them comes with caveats. Carbon isotopes can be pushed around by volcanism, by methane clathrates, by vast peat fires. You can get industrial-looking signals from purely natural chaos. Metal spikes can come from unusual geology, a metal-rich volcanic province, a unique basin that concentrates elements. Not every odd bump in the data means someone was smelting ore. Synthetics are powerful markers, but they're fragile in deep time. A civilization that peaked for a few thousand years, tens or hundreds of millions of years ago, might have left its plastics and composites in rocks that have since been subducted, melted or ground to dust. And that's the other side of the story, the things working against us. Earth is not an archive built for our convenience. It erases as much as it remembers. The crust recycles. Ocean floor is born at ridges and consumed at trenches. Entire mountain chains rise, weather away and vanish. Sediments get folded, metamorphosed, turned into something unrecognizable. The rock record is patchy. Most environments never get preserved at all. Most of what is preserved has gaps. We don't have a perfect high-resolution movie. We have scattered still frames with missing reels in between. On top of that, our sampling is biased. We drill where it's cheap. We study cores from basins that happen to be accessible, stable, and politically convenient. Whole epochs of ocean history may be locked up in sediments we've never touched. So when we say, we see no convincing sign of a prior industrial civilization, what we really mean is, given the rocks we've looked at so far, and the signals we know how to read, nothing demands that explanation. That's a careful, honest kind of ignorance. It leaves room for mystery without inviting every fantasy to move in and claim the space. It also leaves room for wonder, because even if the answer is that we are the first industrial civilization this planet has ever seen, we're not the first dramatic experiment it's run. Before us, there were forests that turned entire atmospheres to oxygen and almost froze the world. There were microbial mats that built reefs like cities. There were amphibians hauling their bodies onto land for the first time, and birds learning to ride the wind over newly built mountain ranges. Deep time is full of stories, full of failures, full of things that lived, changed the world for a moment and disappeared. We may be one more of those things, or we may be the beginning of a much longer chapter. Either way, we're part of that same continuous unfolding. If you're listening to this in the dark, half asleep, you don't have to solve it tonight. You can just imagine that thin line of rock that will one day stand for everything we are. A smear of altered chemistry, a few strange minerals, a scattering of technofossils. Maybe, if we're lucky, a gentle tapering of the worst signals instead of a hard stop. And above it, new layers, new oceans, new forests, maybe new minds before you drift off completely. If you've enjoyed wandering through deep time with me, it really does help to tap like and subscribe so you don't miss the next journey. If you feel like sharing, drop a comment with where you're listening from and what time it is there right now. I love imagining this quiet little community, scattered across the world and across the clock, all falling asleep to the same ancient stories. And if you want to support the channel in the best way, the one that keeps these long, gentle dives into history going, you can listen on Spotify. There's a link waiting in the description. For now, you can let the questions blur at the edges. Some things we can say, some things we can't. Between them is that strange, peaceful space where curiosity lives. The planet will keep turning. The rocks will keep writing. And somewhere, far in the future, someone or something may read our brief chapter and wonder about us the way we wonder now about them.